Hello there, and welcome to a gentle journey through the cosmos. I'm so glad you found your had a long day fill way here tonight. Maybe you have earthbound concerns, or perhaps you're someone who finds peace in contemplating the vast machinery of human ingenuity drifting silently through space. Either way, this evening's voyage is designed just for you. You have nothing to do but settle in. Let your breathing slow and allow your mind to drift as weightlessly as the spacecraft will explore together. Tonight, we're embarking on a quiet expedition through 100 fascinating facts about spacecraft, those remarkable vessels that carry our dreams and discoveries across the infinite darkness. These are not just machines of metal and circuitry, but extensions of human curiosity, floating achievements, drifting through libraries of our greatest universe that still holds countless mysteries. From the delicate precision of orbital mechanics to the everyday miracles of life aboard space stations, we'll discover how these technological marvels have become humanity's quiet ambassadors to the stars. Some of what you'll hear may surprise you, others might spark gentle wonder as you drift towards sleep. And if these calm explorations help you unwind or provide a peaceful way to end your day, consider subscribing to the channel. It helps other restless souls find their way to these quiet cosmic stories, one peaceful night at a time. Now, let's begin our gentle drift through the extraordinary world of spacecraft. Every spacecraft is a time capsule of human ingenuity, carrying within its structure the accumulated wisdom of thousands of engineers, scientists, and dreamers. The design of these vessels begins not with metal and wires, but with questions whispered in the darkness of space. How do we protect fragile human life in a realm where water boils instantly in vacuum? How do we navigate across distances so vast that light itself takes hours to carry our messages home? The answers lie in the patient, methodical work of spacecraft designers who must imagine every possible failure and build solutions into every system. The discipline of spacecraft design emerged quietly in the 1950s and 1960s, born from the urgent dreams of American and Soviet space programs. Unlike the rapid evolution of earthbound technologies, spacecraft design progresses with deliberate caution, each component tested and retested because there are no second chances in the void. Every bolt, every wire, every computer chip must function perfectly for years, or even decades, in an environment more hostile than any place on Earth. The temperature swings alone would destroy most terrestrial machines, with spacecraft surfaces facing the sun reaching over 250 degrees Fahrenheit, while those in shadow plummet to minus 250 degrees. Engineers learned early that to design a spacecraft properly requires what feels like infinite effort, which is why they design them to operate even when things go wrong. This philosophy of fault tolerance means that most deep space missions carry multiple backup systems for every critical function. Computers have twins, communication systems have redundant pathways, and scientific instruments often have backup modes that can continue gathering data even when primary systems fail. It's a quiet form of insurance policy written in silicon and steel, ensuring that the journey continues even when the unexpected inevitably occurs. The International Space Station orbits our planet like a gentle giant, larger than a 6-bedroom house and moving at 17,500 miles per hour. This orbital laboratory represents one of humanity's greatest collaborative achievements, a structure assembled in space by astronauts and cosmonauts working together across cultural and political boundaries. The station's solar array wingspan stretches 356 feet, longer than the world's largest passenger aircraft, automatically tracking the sun as the station completes its 90-minute orbit around Earth. Within this remarkable structure, 8 miles of wire connect the electrical power system, creating a neural network that monitors approximately 350,000 sensors throughout the station. These sensors form a digital nervous system, constantly checking air quality, temperature, pressure, and the health of countless systems that keep the crew safe. The station's computers process this information continuously, alerting controllers on Earth to any anomalies that might require attention, from a simple stuck valve to a degrading battery that needs replacement. Life aboard this orbital home requires a complete reimagining of daily routines. Astronauts wake each morning at 6 a.m. Coordinated Universal Time, beginning their day with a post-sleep inspection of critical systems throughout the station. They check life support systems, verify equipment status, and ensure that nothing has changed during the night hours when Earth's mission controllers were sleeping. This daily ritual provides structure and normalcy in an environment where up and down have no meaning and everything floats freely unless carefully secured. The crew's day begins officially around 8:10 a.m. after breakfast and a daily planning conference with mission control. But perhaps the most crucial part of each day is the 2.5 hours dedicated to exercise. In the weightless environment of space, the human body rapidly loses bone density and muscle mass. Without the constant gentle stress of gravity, bones begin to weaken and muscles atrophy at an alarming rate. The station's exercise equipment includes the advanced resistive exercise device, which uses vacuum cylinders to simulate weightlifting with resistance up to 600 pounds, a treadmill that requires astronauts to wear harnesses and a bungee cords to stay in contact with the running surface, and a stationary bike mounted on shock absorbers to prevent vibrations from disturbing the Yi. Like at experiments elsewhere on the station, even something as simple as personal hygiene becomes an engineering challenge in microgravity. Water doesn't flow downward when there is no down, instead forming floating spheres that drift through the air. Astronauts use special rinseless shampoo, no-rinse body wipes, and edible toothpaste that can be swallowed after brushing. They must brush their teeth with their mouths closed as much as possible to prevent toothpaste from floating away. Even trimming fingernails requires special scissors connected to a vacuum system to prevent nail clippings from floating into sensitive equipment or being inhaled by the crew. The station's life support systems create a closed-loop ecosystem that would seem miraculous to early space pioneers. Daily, each human requires the equivalent of 0.9 kilograms of liquid oxygen and 2.7 kilograms of water. Rather than shipping all these consumables from Earth, the station's environmental control and life support system recycles almost everything. The water recovery system can recycle approximately 93% of all water aboard the station, including humidity condensate and crew urine, processing it into drinking water that is actually purer than most tap water on Earth. Oxygen is generated through the electrolysis of this recycled water, while carbon dioxide scrubbers continuously clean the air to prevent the buildup of this toxic gas. The precision of spacecraft navigation across the solar system requires techniques that seem almost magical. When mission controllers want to communicate with Voyager 1, now more than 14 billion miles from Earth, radio signals take over 22 hours to reach the spacecraft and another 22 hours for any response to return. This incredible delay means that spacecraft must be largely autonomous, capable of making critical decisions without waiting for instructions from Earth. The radio beam from Earth spreads to only about twice the width of our planet by the time it reaches Voyager, demonstrating the remarkable precision required for these cosmic conversations. Modern spacecraft navigation combines multiple sophisticated techniques working in harmony. Inertial measurement units track every twist and turn of the spacecraft's motion through space, while star trackers identify specific constellations to determine precise orientation. Sun sensors help maintain proper alignment, and for missions approaching other planets, optical navigation systems take pictures of destinations and compare them to star charts to calculate exact position and velocity. The most challenging aspect involves planning gravitational assists, where spacecraft must arrive at precisely the right place at exactly the right time to use a planet's gravity as a cosmic slingshot, sometimes planned years in advance of the actual encounter. The robotic arm aboard the International Space Station, known as Canadarm2, demonstrates the remarkable precision possible in the weightless environment of space. This 55-foot mechanical marvel has 7 different joints and 2 end effectors that serve as hands. Capable of moving entire modules weighing over 100 tons, or handling objects as delicate as an egg without cracking the shell. The arm can transport spacewalking astronauts around the station's exterior, deploy science experiments, and perform maintenance tasks that would be impossible for humans to accomplish safely. Recent technological advances aboard the station have opened new possibilities for long-duration space missions. In 2024, the first successful metal 3D printing was conducted in space, depositing a small curve of liquefied stainless steel. This milestone suggests that future spacecraft and space stations might be able to manufacture their own replacement parts, potentially revolutionizing missions to Mars, where resupply from Earth would be impossible. The microgravity environment actually offers advantages for 3D printing, as there is no gravitational distortion of the printing process, allowing for more precise manufacturing of complex geometries than possible on Earth. Even more remarkably, bioprinting experiments have successfully created 3-dimensional human heart tissue samples using specialized equipment designed for the space environment. Tissues printed in microgravity hold their shape without artificial scaffolds, because cells don't settle to the bottom of containers as they do on Earth. These bioprinted tissues could eventually be used to create personalized patches for hearts damaged by disease, representing a convergence of space technology and medical advancement that could benefit both astronauts on long missions and patients on Earth. The International Space Station travels an equivalent distance to the Moon and back approximately once each day, completing 15.5 orbits of Earth during each 24-hour period. This incredible velocity of 17,500 miles per hour means the crew experiences 16 sunrises and sunsets daily, creating a constant cycle of light and darkness that requires artificial lighting schedules to maintain normal sleep patterns. The station's cupola, with its 7 windows, provides breathtaking 360-degree views of our home planet, allowing astronauts to photograph weather systems, city lights at night, and the thin blue line of Earth's atmosphere that protects all life below. As we drift deeper into the realm of spacecraft, we discover that these vessels are more than mere machines. They are humanity's patient explorers, carrying our curiosity across distances that dwarf human comprehension, operating in silence and solitude for years or decades while faithfully transmitting their discoveries back to Earth. In their quiet orbits and distant trajectories, they embody our deepest desire to understand the cosmos and our place within it, one gentle revelation at a time. The story of spacecraft propulsion reads like poetry written in physics, where every action creates an equal and opposite reaction, pushing these vessels through the cosmic void. Chemical rockets provide the thunderous power needed to escape Earth's gravitational embrace, consuming 3 tons of propellant per second in engines like the mighty F1 that powered the Saturn V moonward. These engines generated 1.5 million pounds of thrust each, their turbopumps spinning at 5,500 revolutions per minute. With such ferocity, they could drain a swimming pool in 25 seconds. The roar of their ignition marked humanity's boldest moments, lifting 3,000-ton rockets from launch pads in columns of fire and steam. But once free from Earth's pull, spacecraft often rely on gentler forms of propulsion, electric drives that whisper rather than roar. Ion engines produce thrust no stronger than the weight of a sheet of paper resting on your hand. Yet over months and years, this gentle push can accelerate a spacecraft to incredible velocities. These systems work by ionizing atoms and accelerating them through magnetic fields, creating exhaust velocities 10 times higher than chemical rockets. The patience required for such propulsion mirrors the contemplative nature of deep space exploration itself, where time moves differently and destinations are measured not in miles but in years of travel. Solar sails represent perhaps the most elegant form of spacecraft propulsion, using nothing but the gentle pressure of sunlight to glide through space. These gossamer structures, thin as soap bubbles and larger than football fields, catch photons from the sun like cosmic sailboats riding waves of light. The Advanced Composite Solar Sail System launched in 2024 demonstrates this technology with a sail area 2.5 times larger than previous designs, its silvered surface reflecting sunlight to create thrust without consuming any fuel whatsoever. In the vacuum of space, these craft can accelerate continuously for years, eventually reaching speeds impossible for conventional rockets. The mathematics of orbital mechanics govern every spacecraft's dance through space. Equations that determine whether a vessel will spiral into a planet, escape to the stars, or settle into the perfect elliptical embrace of a stable orbit. These calculations must account for the gravitational pull of multiple bodies, the solar wind that can slowly alter trajectories, and the tiny perturbations caused by the uneven distribution of mass within planets and moons. Mission planners work years in advance to thread spacecraft through gravitational keyholes, using the gravity of planets as cosmic slingshots to reach destinations that would otherwise require impossible amounts of fuel. Jupiter's immense gravity field has served as the ultimate gravitational assist for numerous missions, including the Voyager spacecraft that gained enough velocity from their Jovian encounters to eventually escape the solar system entirely. The precision required for these maneuvers is extraordinary, with spacecraft arriving at specific points in space within windows measured in minutes after journeys lasting years. A small error early in the mission compounds over time and distance, potentially causing a spacecraft to miss its target by millions of miles. Temperature control in spacecraft requires constant vigilance and ingenious engineering solutions. The side of a spacecraft facing the sun can reach temperatures hot enough to melt lead, while surfaces in shadow experience cold more intense than Antarctic winter. Thermal blankets made of multiple layers of reflective material wrap spacecraft like cosmic quilts, each layer carefully spaced to create insulating vacuum gaps. Some missions carry radioisotope thermoelectric generators, devices that convert the heat from radioactive decay into electricity, providing both power and warmth for decades of operation in the outer solar system, where sunlight is too weak to power solar panels. The Voyager spacecraft, launched in 1977 for 4-year missions to Jupiter and Saturn, continue operating nearly 50 years later because of their robust thermal design and redundant systems. These mechanical pilgrims now travel through interstellar space itself, sending back data about the boundary between our solar system and the galaxy beyond. Their plutonium power sources will gradually weaken over the coming years, one by one silencing the instruments that have faithfully reported from the edge of known space for nearly half a century. Communication across interplanetary distances requires patience and precision that stretch human comprehension. Radio signals travel at the speed of light, yet even this cosmic speed limit means that conversations with distant spacecraft unfold over hours rather than seconds. Controllers must plan every command carefully, knowing that by the time they receive confirmation of success or failure, conditions aboard the spacecraft may have already changed. This delay necessitates sophisticated autonomous systems that can diagnose problems and implement solutions without waiting for instructions from Earth. The Deep Space Network, with antennas as large as 230 feet in diameter, maintains these tenuous conversations across billions of miles. These massive dishes track spacecraft across the sky with mechanical precision, their receivers so sensitive they can detect signals weaker than the energy required to light a single Christmas tree bulb. The network operates continuously, with stations in California, Spain, and Australia ensuring that at least one antenna can communicate with any deep space mission as Earth rotates on its axis. Spacecraft must also navigate by the stars themselves, using sophisticated star trackers that identify specific constellations and calculate precise orientation in 3-dimensional space. These electronic astronomers never grow tired or lose focus, constantly updating their readings to maintain perfect alignment with distant targets. Some missions carry sun sensors as backup navigation aids, simple devices that ensure spacecraft can always orient themselves relative to our solar system's central star. The challenge of landing on other worlds requires spacecraft to transform from interplanetary voyagers into precision atmospheric pilots in a matter of minutes. Entry, descent, and landing sequences are often called the 7 minutes of terror because signals take too long to travel between Earth and Mars for real-time control. Spacecraft must autonomously survive atmospheric entry at speeds exceeding 12,000 miles per hour, deploy parachutes at exactly the right altitude, and either airbag bounce or rocket-powered hover to gentle touchdowns on alien surfaces. Japan's Slimlander achieved a remarkable precision landing on the Moon in 2024, touching down within 100 meters of its target despite landing on its side with solar panels facing away from the Sun. This smart lander for investigating the Moon demonstrated advanced navigation systems that could identify lunar features in real time during descent, representing a significant advancement in autonomous spacecraft landing capabilities. Though it operated on battery power for only 1 day due to its awkward orientation, SLIM proved that pinpoint landings on other worlds are possible with sophisticated guidance systems. Robotic spacecraft have become humanity's most successful explorers, visiting every planet in our solar system and revealing landscapes more alien than science fiction writers ever imagined. More than 300 robotic missions have left Earth's orbit, carrying our instruments and curiosity to worlds of incredible diversity. From Mercury's sun-scorched surface to Neptune's methane clouds and supersonic winds, these mechanical ambassadors have shown us beauty and strangeness beyond earthbound imagination. The first interplanetary missions in the 1960s were tentative steps into the cosmic ocean, with Mariner 2's flyby of Venus confirming that our neighboring planet was not the tropical paradise some had hoped for, but rather a hellish world, hot enough to melt lead. Mariner 4's grainy images of Mars revealed a cratered landscape that suggested a planet with complex geological history, rather than the canal-building civilization some had imagined. These early discoveries taught us that the solar system was far stranger and more wonderful than our earthbound perspectives had prepared us to understand. Voyager 2 remains the only spacecraft to visit both Uranus and Neptune, conducting humanity's grand tour of the outer solar system during a rare planetary alignment that occurs only once every 175 years. During its Neptune encounter, the spacecraft discovered that this distant world experiences the fastest winds in the solar system, reaching speeds over 1,200 miles per hour, despite receiving only 1,000th of the sunlight that warms Earth. The mechanics of such atmospheric fury on a world so distant and cold remain one of the many mysteries these robotic explorers have revealed. As these spacecraft drift through the darkness, they carry more than scientific instruments. They bear the hopes and dreams of an entire species, extending human senses across impossible distances to touch worlds we may never visit in person. In their patient orbits and lonely trajectories through interplanetary space, they remind us that curiosity itself is perhaps humanity's greatest spacecraft, capable of crossing any distance and surviving any hardship in pursuit of understanding. The gentle hum of life support systems aboard spacecraft creates a technological lullaby that has serenaded astronauts for decades. These quiet mechanical heartbeats represent thousands of hours of engineering refinement, where every valve, pump, and fan has been designed to operate reliably in the hostile environment of space. The environmental control and life support system aboard the International Space Station processes the breath of its inhabitants continuously, scrubbing carbon dioxide from the air and replacing it with fresh oxygen generated from recycled water. This closed-loop breathing apparatus transforms the station into a self-sustaining bubble of life, floating serenely through the vacuum where no natural atmosphere exists. The station's water recovery system performs daily miracles that would seem impossible to earlier generations of explorers. Every drop of moisture is precious in this orbital laboratory, collected from humidity in the air, recovered from crew perspiration, and even purified from wastewater through sophisticated filtration processes. The recycled water that emerges from these systems often exceeds the purity of municipal water supplies on Earth, processed through multiple stages of filtration and chemical treatment that remove contaminants down to the molecular level. Crew members sometimes joke that today's coffee becomes tomorrow's coffee, but this remarkable recycling represents one of humanity's most successful closed-loop life support achievements. Medical care in space requires innovative approaches to challenges that have no earthbound equivalent. In 2024, a small surgical robot successfully performed simulated procedures aboard the space station, grasping and cutting rubber bands with precision that demonstrated the potential for remote surgery during long-duration missions. This technological milestone addresses one of the most pressing concerns for future expeditions to Mars, where communication delays of up to 24 minutes make real-time surgical guidance from Earth impossible. The robot's delicate manipulations in microgravity suggest that such systems could provide life-saving care to astronauts months or years away from home, extending humanity's reach deeper into the solar system with greater confidence in crew safety. Spacecraft carry within their hulls entire libraries of human knowledge, digital repositories that preserve our greatest achievements and discoveries. The computers aboard these vessels store not only operational software and scientific data, but also music, literature, art, and messages from Earth. The Voyager spacecraft carry golden records containing sounds and images from our planet, including musical selections ranging from classical to jazz, to rock and roll compositions, to folk songs, greetings in dozens of languages, and photographs depicting the diversity of life on Earth. These cultural time capsules drift through interstellar space as ambassadors of human creativity, carrying the essence of our civilization to whatever unknown intelligences might someday encounter them in the cosmic dark. The delicate dance of docking spacecraft demonstrates precision engineering at its most elegant. When supply vessels approach the International Space Station, they must match the orbital velocity of their target exactly, closing the final distance with movements measured in centimeters per second. The station's robotic arm reaches out to grapple these approaching craft, guiding them to docking ports with mechanical grace that masks the incredible complexity of the maneuver. The entire sequence unfolds in slow motion against the backdrop of Earth turning below, a ballet of technology performed at 17,500 miles per hour. Atmospheric processes aboard spacecraft work tirelessly to maintain the perfect balance of gases that sustain human life. Oxygen levels must remain within precise parameters, neither too high to create fire hazards, nor too low to compromise crew health. Carbon dioxide concentrations require constant monitoring, as this invisible gas can accumulate to dangerous levels in the closed environment of a spacecraft. Trace contaminants from equipment outgassing, human metabolism, and maintenance activities must be filtered continuously to prevent the buildup of harmful substances. These atmospheric guardians operate with such reliability that crew members rarely think about the complex chemistry occurring around them with every breath. The thermal regulation systems aboard spacecraft represent some of the most sophisticated temperature control ever devised. Radiators extending from the International Space Station glow faintly in infrared wavelengths as they shed excess heat into the vacuum of space. These panels can be angled to optimize heat rejection while avoiding shadows that might freeze critical components. Internal temperature control relies on circulating fluids that transport heat from equipment-dense areas to radiator panels, creating thermal highways that distribute warmth throughout the station's modules. Some areas require heating to prevent sensitive electronics from freezing, while others need active cooling to protect equipment from overheating. Scientific instruments aboard spacecraft push the boundaries of measurement and detection beyond anything possible on Earth. Spectrometers can identify the chemical composition of distant worlds by analyzing reflected sunlight, revealing the presence of water, methane, and other molecules across millions of miles of space. Magnetometers detect the invisible magnetic fields that surround planets and moons, mapping these protective barriers that shield worlds from harmful radiation. Particle detectors count and categorize the atomic fragments that stream through space, providing insights into cosmic processes that occur on scales both microscopic and galactic. The psychological challenges of spacecraft operation extend far beyond the technical demands of keeping complex systems running. Astronauts must adapt to living in confined spaces for months at a time, working closely with the same small group of colleagues while separated from friends and family by the vast emptiness of space. The view of Earth from orbit provides both comfort and perspective, reminding crew members of their connection to the planet below, while emphasizing their isolation in the cosmic void. Spacecraft designers have learned to include windows not just for operational visibility, but for the mental health benefits that come from seeing the stars and watching Earth pass by in its eternal rotation. Communication delays shape every aspect of deep space mission operations, creating a unique form of patience that ground controllers must master. Commands sent to Mars rovers during conjunction periods, when the Sun blocks direct radio paths, must be uploaded days in advance and stored in the spacecraft's memory until conditions allow transmission. Mission planners develop elaborate timelines that account for these communication blackouts, ensuring that robotic explorers can continue their work autonomously while maintaining the flexibility to respond to unexpected discoveries or equipment problems. The power systems aboard spacecraft represent marvels of efficiency and longevity that far exceed most terrestrial applications. Solar panels must continue generating electricity for decades, while exposed to temperature extremes, radiation, and micrometeorite impacts that would quickly destroy conventional photovoltaic systems. Radioisotope thermoelectric generators provide steady power for missions to the outer solar system, converting the heat from radioactive decay into electricity with no moving parts to wear out or break. These nuclear batteries can operate for decades, gradually declining in output as their radioactive fuel slowly decays, but providing reliable power long after chemical batteries would have been exhausted. Spacecraft manufacturing requires clean room facilities that maintain air purity levels exceeding those found in hospital operating theaters. Every component must be meticulously cleaned and tested before installation, as contamination that might be harmless on Earth could outgas in vacuum conditions and coat sensitive optical instruments or electronic components. Technicians work in specialized garments that prevent human skin cells, hair, and oils from contaminating spacecraft surfaces. The assembly process can take years, with each subsystem thoroughly tested individually before integration into the complete vehicle. The guidance systems aboard spacecraft combine multiple navigation techniques with elegant redundancy. Star trackers identify celestial landmarks with extraordinary precision, using catalogs containing the positions of thousands of stars to determine spacecraft orientation to within fractions of degrees. Inertial measurement units sense every acceleration and rotation, integrating these measurements over time to track position and velocity even when external references are unavailable. Sun sensors provide backup orientation data, ensuring that spacecraft can maintain proper alignment even if primary navigation systems fail. Launch vehicles that carry spacecraft into orbit represent controlled explosions of extraordinary precision and power. The first stage engines of major rockets consume tons of propellant per second, generating millions of pounds of thrust that must be precisely controlled to guide these massive vehicles through the atmosphere. The transition from first to second stage occurs in seconds, with explosive bolts severing connections and igniting new engines, while the rocket continues its ascent through increasingly thin air. Upper stages must restart their engines in the vacuum of space, sometimes after coasting for hours in unpowered flight, demonstrating remarkable reliability in the most demanding environment imaginable. Spacecraft testing involves subjecting these precious vehicles to conditions more severe than anything they will encounter during actual missions. Thermal vacuum chambers simulate the temperature extremes and vacuum of space, while vibration tables shake spacecraft with forces that exceed those experienced during launch. Acoustic chambers subject vehicles to sound levels that would be physically painful to humans, testing their ability to survive the intense noise generated by rocket engines during ascent. Every test pushes spacecraft systems to their limits and beyond, ensuring that the vehicles that venture into space can survive whatever the cosmos might present. The legacy systems aboard long-duration missions like Voyager rely on computer technology that was cutting edge in the 1970s, but now seems primitively simple compared to modern smartphones. These spacecraft computers contain less processing power than a digital watch, yet they continue to operate flawlessly after decades in the harsh environment of space. Their reliability stems from robust design principles that prioritize fault tolerance over raw computational speed, with multiple backup systems and conservative operating margins that have allowed them to function far longer than their original mission requirements. Orbital debris tracking has become an essential aspect of spacecraft operations, with thousands of fragments from past missions creating a hazardous environment in the most useful orbital altitudes around Earth. Ground-based radar systems monitor objects larger than a softball, providing warnings when debris threatens active spacecraft. The International Space Station occasionally must adjust its orbit to avoid predicted collisions, using thrusters to nudge the massive structure into a slightly different path. Some debris is too small to track, but large enough to damage spacecraft, creating a persistent background risk that mission planners must consider for every orbital operation. The miniaturization of spacecraft components has enabled entire classes of missions that would have been impossible with earlier technology. CubeSats, small satellites no larger than a loaf of bread, can now carry sophisticated instruments that rival those flown on much larger spacecraft decades ago. These diminutive explorers can be launched as secondary payloads, riding along with larger missions to reach orbit at a fraction of the traditional cost. Some CubeSats have demonstrated interplanetary capabilities, proving that significant scientific discoveries are possible even with severely constrained budgets and timelines. Spacecraft operations centers maintain continuous vigilance over their mechanical charges, with teams of specialists monitoring telemetry data that streams back from orbit and beyond. These ground controllers become intimately familiar with the personalities of their spacecraft, learning to recognize subtle changes in system behavior that might indicate developing problems. The relationship between controllers and their spacecraft develops over years of operation, creating an almost personal connection between humans and machines separated by millions of miles of empty space. As these remarkable vessels continue their patient journeys through the cosmos, they carry with them not just scientific instruments and engineering systems, but the dreams and aspirations of an entire species. Each spacecraft represents humanity's desire to explore beyond the familiar boundaries of our world, to seek understanding in the vast darkness that surrounds our small planet. In their quiet orbits and distant trajectories, they remind us that the universe is both larger and more wonderful than we ever imagined, filled with mysteries that call to our deepest curiosity and invite us to reach ever further into the cosmic night. The art of spacecraft construction unfolds in facilities that resemble cathedrals of technology, where every surface gleams under carefully controlled lighting, and the air itself is purer than mountain springs. These clean rooms maintain atmospheric conditions more sterile than surgical theaters, with technicians moving through their work like gentle ghosts in protective garments that shield their mechanical patients from the smallest contamination. A single human hair or flake of skin could compromise delicate optical systems, so every breath is filtered, every movement deliberate and precise. Within these sanctuaries, spacecraft take shape over months and years, assembled with the patience of watchmakers crafting timepieces that must tick perfectly for decades. Each component arrives wrapped in protective materials, having traveled its own journey through quality assurance processes that would seem obsessive if the stakes were not so absolute. There are no repair shops in the vacuum of space, no mechanics who can be summoned to fix a broken part millions of miles from home. Every bolt must be perfect, Every wire connection flawless, every circuit board capable of operating through temperature swings that would shatter ordinary electronics. The testing phase subjects these mechanical voyagers to ordeals that exceed anything they will encounter during their actual missions. Vibration tables shake spacecraft with forces that simulate rocket launches, while the vehicles are monitored by sensors that measure every tremor and stress. The thunderous roar of acoustic chambers subjects them to sound levels that would damage human hearing, testing their ability to survive the intense noise generated during ascent through Earth's atmosphere. Thermal chambers cycle them through temperature extremes from Arctic cold to desert heat, ensuring that every system can function whether facing the sun's fierce radiation or the absolute cold of interstellar shadow. Yet perhaps the most remarkable test is simply time itself. Some spacecraft undergo years of preparation, their systems powered up and monitored continuously, while engineers verify that every component ages gracefully. Electronics that will operate for decades in space must prove their longevity here on Earth, running through countless cycles, while technicians watch for the subtle signs of degradation that might spell mission failure years hence. This patient vigil represents one of quality of the most demanding forms assurance ever devised, where the price of failure is measured not just in dollars, but in lost opportunities to expand human knowledge. The moment of launch transforms these carefully crafted vessels from stationary artifacts into dynamic entities hurtling through space atop columns of fire and thunder. The forces experienced during ascent would crush a human body, yet spacecraft must survive these violent accelerations while maintaining perfect alignment and protecting their delicate instruments. The transition from Earth's protective atmosphere to the harsh vacuum of space occurs in minutes. But the preparation for this journey spans years of meticulous planning and testing. Once free from Earth's gravitational embrace, spacecraft begin their true existence as independent entities navigating the cosmic ocean. Their guidance systems awaken to the challenge of determining position and orientation, using only the stars as reference points. These electronic navigators carry within their memory banks the precise positions of thousands of celestial landmarks, creating three-dimensional maps of the cosmos that allow them to know exactly where they are and which direction they face, even when separated from Earth by billions of miles. The power systems that sustain these far-traveled machines represent engineering achievements that far exceed most Earthbound applications. Solar panels must continue generating electricity for decades while bombarded by radiation that would quickly destroy conventional photovoltaic cells. The panels themselves are works of art, their crystalline surfaces arranged in perfect geometric patterns that track the sun with mechanical precision. As spacecraft venture farther from our solar system's central star, these panels must extract energy from increasingly faint sunlight, their efficiency measured against the ultimate challenge of powering complex systems on the energy equivalent of distant starlight. For missions to the outer reaches of the solar system, where sunlight becomes too weak to sustain operations, spacecraft carry nuclear batteries that convert radioactive decay into electricity. These radioisotope thermoelectric generators require no moving parts, no maintenance, no fuel beyond the slowly diminishing atomic nuclei within their cores. They represent perhaps the most patient power sources ever created, designed to operate continuously for decades, while their output gradually declines in perfect accordance with the mathematical laws that govern atomic decay. Communication systems aboard distant spacecraft must transmit their discoveries across distances that challenge human comprehension. Radio signals carrying scientific data and engineering telemetry spread out as they travel, becoming fainter with each million miles until they arrive at Earth as whispers barely distinguishable from cosmic background noise. The receivers that capture these faint signals represent miracles of electronic sensitivity, able to extract meaningful information from transmissions weaker than the energy required to power a single LED. The antennas that maintain these cosmic conversations are themselves marvels of mechanical engineering, structures as large as sports stadiums that must track spacecraft moving across the sky with precision measured in fractions of degrees. These massive dishes rotate slowly but relentlessly, their servo systems adjusting continuously to maintain perfect alignment with targets that may be billions of miles away. The operators who control these systems develop an almost mystical relationship with the spacecraft they track, learning to recognize the subtle changes in signal strength that indicate whether their distant charges are healthy or experiencing problems. Data compression aboard spacecraft transforms raw scientific measurements into efficient digital packages that can survive the long journey back to Earth. Images that would fill entire computer hard drives are reduced to streams of numbers that capture every essential detail while eliminating redundant information. This process requires sophisticated algorithms that run continuously aboard spacecraft computers, making split-second decisions about which data is most important and how to preserve maximum scientific value within limited transmission windows. The software that controls spacecraft operations represents some of the most reliable programming ever written, code that must function flawlessly for years without updates or patches. These programs are tested more thoroughly than any Earthbound application, run through millions of simulated scenarios to verify correct operation under every conceivable condition. The programmers who write this code know that their work will operate autonomously in the most hostile environment imaginable, making decisions that could determine mission success or failure with no possibility of human intervention. Attitude control systems maintain spacecraft orientation with precision that exceeds the steadiest human hand. Reaction wheels spin silently within these vessels, their rotating masses creating gyroscopic forces that can turn multi-ton spacecraft with movements measured in fractions of degrees. When these mechanical gyroscopes reach their limits, small thrusters fire brief puffs of compressed gas, nudging the spacecraft back to perfect alignment while simultaneously desaturating the reaction wheels for continued operation. The thermal management systems aboard spacecraft work continuously to maintain equipment temperatures within narrow operating ranges despite the extreme environment of space. Heaters warm critical components during long passages through planetary shadows, while radiators shed excess heat generated by electronic systems and scientific instruments. Multi-layer insulation blankets wrap spacecraft like cosmic quilts, their reflective surfaces bouncing thermal radiation away while trapping essential warmth within. These thermal control systems must function automatically, adjusting to changing conditions as spacecraft move through different regions of space, where thermal loads vary dramatically. Scientific instruments aboard these mechanical explorers extend human sensors across impossible distances, detecting phenomena that no Earthbound observer could ever experience directly. Spectrometers analyze the chemical composition of distant worlds by examining reflected sunlight, revealing the presence of water, methane, and other molecules that tell stories of alien geology and possible biology. Magnetometers map the invisible magnetic fields that surround planets and moons, these protective shields that deflect harmful radiation and shape the space environment around celestial bodies. Particle detectors count and categorize the atomic fragments that stream through space, measuring cosmic rays that carry information about stellar explosions and galactic processes occurring thousands of light years away. These instruments operate with sensitivity that borders on the miraculous, detecting individual atomic nuclei traveling at nearly the speed of light, while distinguishing between different types of particles based on their energy and trajectory. Cameras aboard spacecraft capture images that have revolutionized human understanding of our place in the cosmos. These electronic eyes see wavelengths of light invisible to human vision, revealing details of planetary surfaces, atmospheric phenomena, and cosmic structures that would otherwise remain hidden. The images they transmit back to Earth often take hours or days to arrive, depending on the distance involved. But each photograph represents a moment frozen in time from worlds that humans may never visit in person. The computer memory systems that store these images and scientific measurements must operate reliably for decades in an environment where cosmic rays radiation can flip individual bits of data without warning. Error correction algorithms work continuously to detect and repair these cosmic-induced errors, ensuring that precious scientific data survives the journey back to Earth intact. Some spacecraft carry multiple copies of critical data, storing identical information in separate memory banks as insurance against catastrophic system failures. Navigation through the solar system requires understanding gravitational forces that operate on scales both intimate and vast. Spacecraft trajectory planners must account for the gravitational pull of every major body in the solar system, calculating how these invisible forces will bend flight paths over months and years of interplanetary travel. The mathematics involved in these calculations fill entire textbooks, equations that describe the complex dance of celestial mechanics with precision that allows spacecraft to arrive at distant targets within windows measured in minutes after journeys lasting years. Gravitational assists, where spacecraft use planetary gravity as cosmic slingshots, represent perhaps the most elegant form of space navigation ever devised. These maneuvers require arriving at precisely calculated points in space at exactly the right time, threading through gravitational keyholes that exist for only brief windows. The energy gained from these encounters comes from the orbital motion of the planets themselves, borrowing infinitesimal amounts of momentum from worlds whose masses dwarf the spacecraft by factors of trillions. The Voyager missions demonstrated the ultimate expression of this technique, using a rare alignment of the outer planets to conduct humanity's grand tour of the solar system. The gravitational assists these spacecraft received from Jupiter, Saturn, Uranus, and Neptune provided enough energy to eventually escape the solar system entirely, sending these robotic ambassadors into interstellar space, carrying messages from Earth to whatever unknown civilizations might someday encounter them in the cosmic dark. Autonomous decision-making systems aboard modern spacecraft can diagnose problems and implement solutions without waiting for instructions from Earth. These artificial intelligence systems monitor thousands of parameters continuously, learning to recognize patterns that indicate developing problems before they become critical. When anomalies are detected, the spacecraft can automatically switch to backup systems, adjust operating modes, or even place itself in a protective safe mode until ground controllers can assess the situation and provide detailed instructions. The longevity of spacecraft systems often exceeds the wildest expectations of their designers. Missions planned for months or years continue operating for decades, their components aging gracefully in the stable environment of space, where there is no weather to cause corrosion, no oxygen to promote oxidation, and no gravity to stress mechanical joints. The primary threats to spacecraft longevity are radiation damage and the gradual failure of electronic components, but careful design and component selection can extend operational lifetimes far beyond original specifications. Redundancy pervades every aspect of spacecraft design, with backup systems for backup systems ensuring that single-point failures cannot end missions. Critical computers often operate in triplets, with majority voting determining correct operations when one unit begins to fail. Communication systems include multiple transmitters and receivers, any one of which can maintain contact with Earth if the others malfunction. Even scientific instruments often include backup modes that can continue gathering data at reduced capability if primary systems fail. The ground support equipment that monitors and controls spacecraft operations represents the earthbound half of these space exploration partnerships. Mission control centers operate continuously, with teams of specialists monitoring telemetry streams that carry information about spacecraft health and scientific discoveries. These controllers develop intimate knowledge of their mechanical charges, learning to interpret subtle changes in system behavior that might indicate developing problems or new opportunities for scientific investigation. Deep space communication networks span the globe, ensuring that at least one massive antenna can maintain contact with distant spacecraft as Earth rotates. These facilities represent some of the most sensitive radio receivers ever constructed, able to detect signals so weak they would be overwhelmed by the energy from a single snowflake hitting the antenna. The operators who maintain these systems work with equipment that pushes the absolute limits of electronic sensitivity, amplifying whispers from the cosmic dark until they can be decoded into scientific data and engineering tell further into contemplation of the cemetery. As we drift remarkable machines, we begin to understand that spacecraft represent more than mere collections of metal, silicon, and software. They embody humanity's deepest aspirations, our desire to reach beyond the comfortable boundaries of our home world and touch the infinite mystery that surrounds us. In their patient journeys through the cosmic night, they carry not just scientific instruments, but the dreams and hopes of our entire species, mechanical expressions of the curiosity that drives us to explore, to discover, and to understand our place in the vast tapestry of existence. The quiet rhythm of spacecraft housekeeping creates a technological symphony that plays continuously in the background of space exploration. These automated systems perform thousands of small tasks each day, monitoring temperatures, adjusting power distribution, and maintaining the delicate balance of systems that keep these mechanical voyagers alive. Like digital custodians, they work tirelessly to prevent the accumulation of small problems that could cascade into mission-threatening failures. The beauty lies in their invisibility, performing essential maintenance tasks so seamlessly that human operators rarely need to intervene. Microprocessors aboard spacecraft operate in an environment where a single cosmic ray can flip a bit of memory, potentially causing catastrophic system failures. To combat this invisible threat, spacecraft computers employ sophisticated error detection and correction algorithms that work continuously in the background. These systems can detect when radiation has altered stored data and automatically restore the correct information from backup copies. Some spacecraft carry 3 identical computers that vote on every decision, ensuring that if one unit is damaged by radiation, the other 2 can continue operating normally. The evolution of spacecraft computers tells a story of remarkable miniaturization and increased capability. Early space missions relied on computers less powerful than modern calculators, yet these primitive systems successfully navigated to the Moon and guided spacecraft to other planets. Today's missions carry computers millions of times more powerful, yet they still operate on the same fundamental principles of redundancy and fault tolerance that kept those early pioneers functioning far beyond their planned lifetimes. Data storage systems aboard spacecraft must preserve scientific measurements and images for months or years before transmission opportunities arise. These digital memories operate in temperature extremes that would destroy ordinary computer components, using specially hardened electronics that can function from the heat of Mercury to the cold of interstellar space. Some missions carry multiple copies of critical software and data distributed across separate storage systems to ensure that no single failure can destroy irreplaceable scientific information. The scheduling systems that control spacecraft operations work like invisible conductors, orchestrating complex sequences of activities across days, weeks, and months. These automated schedulers must balance competing demands for power, data storage, and communication time while ensuring that scientific observations occur at precisely the right moments. They account for the changing positions of planets, the orientation requirements of different instruments, and the limited windows when Earth-based antennas can receive transmissions from distant spacecraft. Propulsion systems aboard interplanetary missions often remain dormant for years between critical maneuvers, yet they must ignite reliably when commanded to make course corrections or orbital insertions. The engineering challenge of creating rocket engines that can sit unused in the harsh environment of space and then fire perfectly on demand requires materials and designs that far exceed terrestrial standards. Propellant lines must remain unclogged despite temperature cycling, valves must seal perfectly despite years of thermal stress, and combustion chambers must ignite cleanly after extended dormancy. The fuel efficiency of spacecraft propulsion systems would astound automotive engineers, with some missions traveling billions of miles while consuming less fuel than a cross-country automobile trip. This remarkable efficiency comes from the physics of space travel, where there is no atmospheric drag to overcome, and small velocity changes can redirect spacecraft to entirely different destinations. Ion drives achieve the ultimate expression of this efficiency, accelerating spacecraft to incredible velocities using amounts of propellant that could fit in a small suitcase. Attitude determination systems aboard spacecraft combine multiple sensors to maintain precise knowledge of orientation in three-dimensional space. Star trackers photograph the sky and compare their images to onboard star catalogues, determining spacecraft pointing with accuracy measured in thousandths of degrees. Sun sensors provide backup orientation data, while inertial measurement units track every rotation and acceleration to maintain continuous awareness of spacecraft motion even when external references are temporarily unavailable. The gyroscopic systems that control spacecraft orientation operate on principles that seem almost magical, using the conservation of angular momentum to turn massive vehicles with precise, gentle movements. Reaction wheels spin silently within spacecraft, their rotating masses creating forces that can reorient multi-ton vehicles with movements more delicate than a dancer's gesture. When these wheels reach their speed limits, small thrusters fire brief puffs of gas to desaturate them while simultaneously adjusting spacecraft pointing. Thermal vacuum chambers on Earth simulate the extreme environment that spacecraft will encounter in space, subjecting these vehicles to temperature swings and vacuum conditions that exceed anything they will experience during actual missions. These massive facilities can recreate the temperature of interstellar space while simultaneously exposing spacecraft to simulated solar radiation, testing every system under conditions more severe than the real space environment. The testing process can take months, with spacecraft operating continuously, while engineers monitor every component for signs of degradation or failure. Contamination control during spacecraft assembly requires protocols more stringent than pharmaceutical manufacturing, with every component cleaned and verified before installation. Technicians work in specialized clean rooms wearing protective garments that prevent human contamination from reaching sensitive spacecraft surfaces. Even the air is filtered to remove particles smaller than the wavelength of visible light, creating an environment cleaner than a hospital operating room. The quality assurance processes for spacecraft components involve testing procedures that would seem obsessive if the stakes were not so absolute. Electronic components undergo burn-in testing where they operate continuously at elevated temperatures to weed out parts that might fail during extended space missions. Mechanical components are cycled through thousands of operations to verify their longevity, while materials are subjected to radiation doses that simulate decades of space exposure compressed into weeks of laboratory testing. Launch vehicle integration represents one of the most delicate phases of spacecraft preparation, where these carefully crafted machines are mated to rockets that will subject them to forces equivalent to several times their own weight. The spacecraft must be perfectly balanced and securely attached to survive the violent acceleration of launch, while remaining isolated from the intense vibrations generated by rocket engines. Shock absorbers and dampening systems protect delicate instruments from the acoustic environment created during ascent through Earth's atmosphere. The countdown procedures for spacecraft launches involve thousands of individual checkpoints, each one verified before the sequence can continue. These protocols ensure that every system is functioning perfectly before committing to the irreversible act of launch. Weather conditions must be within narrow limits. Ground support equipment must be operating flawlessly, and tracking stations around the world must be ready to monitor the spacecraft's initial orbit. The final moments before ignition represent the culmination of years of preparation, compressed into a few tension-filled seconds. Orbital insertion maneuvers require spacecraft to fire their engines at precisely calculated moments to achieve the exact velocity needed for stable orbit around their destination. The timing windows for these burns are often measured in seconds, with delays or premature ignition potentially causing the spacecraft to crash into the planet or escape into interplanetary space. The mathematics involved in calculating these maneuvers must account for the gravitational influences of multiple bodies, atmospheric drag if present, and the changing mass of the spacecraft as it consumes fuel. The scientific planning processes for spacecraft missions begin years before launch, with researchers from around the world collaborating to design observation sequences that will maximize the scientific return from these expensive expeditions. Every minute of spacecraft time is precious, requiring careful coordination between different investigation teams, who must share limited resources, including power, data storage, and communication time with Earth. The resulting observation plans represent compromises between competing scientific priorities, optimized to address the most important questions while maintaining flexibility for unexpected discoveries. Calibration procedures for spacecraft instruments ensure that measurements made millions of miles from Earth remain accurate and meaningful. These processes often begin before launch, with instruments characterized in laboratory conditions that can be precisely controlled and repeated. Once in space, periodic calibration observations of known targets allow scientists to track instrument performance and correct for any degradation that might occur during the mission. The data analysis pipelines that process information from spacecraft instruments represent some of the most sophisticated scientific computing systems ever created. Raw measurements from space must be converted into meaningful scientific data through complex algorithms that account for instrument characteristics, spacecraft motion, and environmental conditions. These processing systems often operate automatically, producing calibrated data products that scientists around the world can access within hours or days of the original observations. Spacecraft mission extensions often push these vehicles far beyond their original design specifications, operating instruments and systems for years longer than originally planned. The decision to continue missions beyond their planned lifetimes requires careful assessment of remaining consumables, system health, and scientific potential. Some of the most significant discoveries in space exploration have come from extended missions that continued operating long after their primary objectives were completed. The international cooperation required for major spacecraft missions brings together scientists, engineers, and organizations from dozens of countries, creating partnerships that transcend political boundaries. These collaborations demonstrate humanity's ability to work together toward common goals, pooling resources and expertise to achieve objectives that no single nation could accomplish alone. The success of these partnerships provides a model for future endeavors that will require even greater international cooperation as we venture deeper into the solar system. Communication protocols between spacecraft and Earth have evolved into sophisticated languages that maximize the efficiency of data transmission across interplanetary distances. These protocols compress scientific measurements and engineering data into compact formats that can survive the noise and interference present in deep space communications. Error correction codes ensure that transmitted data arrives intact, even when signals are so weak they are barely distinguishable from cosmic background radiation. The antenna systems aboard spacecraft represent marvels of mechanical engineering, structures that must unfold or deploy with perfect precision after months or years of space travel. These antennas often fold into compact configurations for launch, then extend to their full size, using mechanisms that must work flawlessly, despite exposure to temperature extremes, radiation, and the vacuum of space. The pointing accuracy of these antennas must be maintained to fractions of degrees to ensure reliable communication with Earth-based receivers. Power management systems aboard spacecraft continuously balance the energy demands of different subsystems, automatically adjusting power distribution as conditions change. Solar panels may be shadowed during planetary eclipses, batteries may degrade over time, and scientific instruments may require varying amounts of power depending on their operating modes. These power systems must maintain stable voltages and currents despite these changing conditions. ensuring that critical systems continue operating even during periods of reduced power generation. The psychological aspects of spacecraft operations affect both the human crews aboard manned missions and the ground controllers who monitor robotic explorers. Living and working in the confined environment of a spacecraft requires mental resilience and adaptability that few Earthbound occupations demand. Ground controllers develop emotional attachments to their robotic charges, celebrating successful observations and worrying about system anomalies as if the spacecraft were living creatures rather than mechanical devices. Environmental monitoring systems aboard spacecraft track thousands of parameters that indicate the health and status of these complex machines. Temperature sensors monitor critical components. Pressure gauges track propellant tank conditions, and voltage monitors ensure that electrical systems are functioning properly. This telemetry data streams back to Earth continuously, allowing ground controllers to diagnose problems and plan corrective actions before minor issues become mission-threatening failures. The legacy of spacecraft exploration extends far beyond the scientific discoveries and technological achievements of individual missions. These mechanical ambassadors have fundamentally changed humanity's perspective on our place in the universe, providing images and measurements that reveal both the beauty and the hostility of the cosmic environment. They have shown us worlds of incredible diversity, from the sulfur volcanoes of Io to the methane lakes of Titan, expanding our understanding of the conditions under which life might exist beyond Earth. Future spacecraft missions will push even further into the unknown, carrying increasingly sophisticated instruments to destinations that remain largely mysterious. Missions to the outer moons of the giant planets will search for signs of life in subsurface oceans, while interstellar probes will eventually carry human-made objects beyond the influence of our Sun for the first time in history. These future explorers will build upon the achievements of their predecessors, extending humanity's reach ever deeper into the cosmic ocean. The manufacturing techniques used to create spacecraft components often lead to advances that benefit terrestrial applications, with space-qualified materials and processes finding their way into everything from medical devices to consumer electronics. The demanding requirements of space missions drive innovation in ways that more forgiving Earthbound applications cannot, pushing engineers to develop solutions that are lighter, more reliable, and more efficient than anything previously achieved. Quality control procedures for spacecraft manufacturing involve documentation and traceability requirements that exceed those found in any other industry. Every component can be traced back to its original materials, manufacturing processes, and test results, creating a complete pedigree that allows engineers to understand exactly how each part was created and validated. This level of documentation enables detailed failure analysis if problems occur, helping to prevent similar issues in future missions. The testing facilities used to qualify spacecraft for space missions represent some of the most sophisticated simulation environments ever created. Acoustic chambers can generate sound levels that would be physically dangerous to humans, while vibration tables can shake spacecraft with forces that simulate rocket launches. Thermal vacuum chambers recreate the temperature extremes and vacuum conditions of space, allowing engineers to verify that every system will function properly in the harsh environment beyond Earth's atmosphere. As these mechanical explorers continue their patient journeys through the darkness between worlds, they carry with them the dreams and aspirations of our entire species. Each successful mission represents a triumph of human ingenuity over the challenges of distance, time, and the hostile environment of space. In their quiet orbits and distant trajectories, they remind us that curiosity itself may be humanity's greatest achievement, driving us to reach beyond the familiar boundaries of our world in search of understanding and wonder. The gentle hum of spacecraft systems creates a technological lullaby that has accompanied human space travelers for decades, while robotic explorers drift in perfect silence through the vacuum, their electronic heartbeats detectable only through radio waves that whisper across the cosmic distances. In this peaceful contemplation of humanity's greatest machines, we find ourselves drawn into the same sense of wonder that drives these vessels ever outward, seeking answers to questions we have only begun to learn how to ask. The art of spacecraft maintenance unfolds like a silent symphony in the depths of space, where robotic systems perform countless tiny adjustments without human intervention. Gyroscopes drift slowly over months and years, requiring periodic correction through gentle thruster pulses that consume mere grams of precious fuel. Battery management systems balance charge cycles with mathematical precision, ensuring that power storage remains optimal despite temperature fluctuations that would challenge any Earthbound device. These automated caretakers work tirelessly in the background, their algorithms fine-tuned through decades of spaceflight experience to anticipate problems before they manifest. The delicate choreography of multi-spacecraft missions creates celestial ballets that unfold over years of coordinated flight. Formation flying requires vehicles to maintain precise relative positions, despite the complex gravitational influences of planets and moons. Each spacecraft must adjust its trajectory independently, while remaining synchronized with, creating geometric its companions' patterns that drift slowly through space, like mechanical constellations. The mathematics governing these formations account for perturbations so subtle they would be invisible to casual observation, yet significant enough to disrupt the mission if left uncorrected. Dust mitigation systems aboard spacecraft protect sensitive components from the microscopic debris that pervades interplanetary space. These particles, smaller than grains of sand, can sandblast optical surfaces and penetrate electronic housings over time. Protective shields and covers deploy automatically to safeguard critical instruments during high-velocity encounters, while electrostatic systems repel charged particles that might otherwise accumulate on spacecraft surfaces. The engineering required to predict and counter these invisible threats demonstrates the extraordinary attention to detail that space missions demand. Sample collection mechanisms on robotic explorers represent some of the most sophisticated remote manipulation ever achieved. Robotic arms extend across alien landscapes, with movements choreographed from millions of miles away. Their operations planned months in advance to account for communication delays. Drilling systems bore into rock formations that have remained undisturbed for billions of years, extracting cores that preserve the geological history of distant worlds. These samples are processed through miniaturized laboratories that rival Earthbound facilities in their analytical capabilities, all contained within packages no larger than briefcases. The atmospheric entry systems that guide spacecraft through planetary atmospheres must function flawlessly during the brief, violent transition from interplanetary space to surface operations. Heat shields endure temperatures that would vaporize most materials, their ablative surfaces designed to carry away thermal energy through controlled erosion. Parachute systems deploy in precise sequences, their timing calculated to achieve gentle touchdowns, despite atmospheric conditions that may vary dramatically from mission models. The entire entry, descent, and landing sequence often unfolds in less than 10 minutes, yet requires years of preparation and testing. Cryogenic systems aboard spacecraft maintain scientific instruments and samples at temperatures approaching absolute zero, creating pockets of deep cold in the vast warmth of interplanetary space. These thermal isolation systems use multiple layers of insulation and active cooling to preserve the quantum states necessary for certain measurements. Liquid helium and hydrogen dewars maintain their precious contents for years, their cooling systems operating with efficiency that far exceeds any terrestrial refrigeration technology. The gradual warming of these systems often determines mission lifetimes, as instruments requiring extreme cold cease operations when cryogenic supplies are exhausted. The precision timing systems that coordinate spacecraft operations rely on atomic clocks that maintain accuracy to billionths of a second, despite the relativistic effects of high-speed travel through varying gravitational fields. These timepieces synchronize observations across multiple spacecraft, enabling interferometric measurements that combine data from vehicles separated by thousands of miles. Time itself becomes a scientific instrument, with nanosecond precision enabling ranging measurements that determine spacecraft positions to within meters across interplanetary distances. Adaptive software systems aboard modern spacecraft learn from experience, modifying their behavior based on environmental conditions and system performance. Machine learning algorithms optimize power consumption, adjust instrument settings for changing observational targets, and even predict component failures before they occur. These artificial intelligence systems operate autonomously for months at a time, making thousands of small decisions that collectively determine mission success. The software continues evolving throughout the mission lifetime, becoming more efficient and capable as it accumulates operational experience. The miniaturized chemistry laboratories aboard sample analysis missions can identify molecular compositions with precision that rivals major research facilities on Earth. Spectrometers, smaller than textbooks, can detect trace elements in concentrations measured in parts per billion, while chromatography systems separate complex chemical mixtures for individual analysis. These instruments operate in vacuum conditions and temperature extremes that would destroy conventional laboratory equipment, yet maintain calibration accuracy for years of continuous operation. Magnetic field generators aboard some spacecraft create artificial magnetospheres that deflect charged particles and protect sensitive electronics from radiation damage. These magnetic shields operate continuously, their field strengths carefully calibrated to provide protection without interfering with scientific measurements. The power required to maintain these protective fields represents a significant portion of spacecraft electrical budgets, yet the protection they provide enables missions that would otherwise be impossible in high radiation environments. The deployable structures aboard spacecraft unfold like mechanical origami, transforming from compact launch configurations to their full operational geometry through sequences of precisely timed movements. Solar panel arrays extend to sizes that dwarf the spacecraft bus, while antenna reflectors bloom into parabolic surfaces meters across. These deployment mechanisms must function reliably after months or years in the dormant state, their springs and motors operating in vacuum conditions that would challenge any terrestrial machinery. Contamination prevention protocols ensure that spacecraft exploring potentially habitable worlds do not inadvertently introduce earthly microorganisms to pristine alien environments. Sterilization procedures subject entire spacecraft to heat treatments that would kill any terrestrial life, while cleanroom assembly prevents biological contamination during construction. These planetary protection measures require documentation of every component's biological burden and verification that contamination levels remain below strict international standards throughout the mission lifecycle. The optical systems aboard spacecraft telescopes achieve image quality that exceeds ground-based observatories despite operating in the harsh environment of space. Mirror surfaces maintain their precision geometry despite temperature cycling that would warp terrestrial optics, while pointing systems track celestial targets with stability measured in milliarc seconds. These space-based observatories can stare at single targets for hours or days without atmospheric interference, accumulating photons from sources so distant their light began its journey billions of years ago. Propellant gauging systems determine remaining fuel quantities through techniques that work reliably in the weightless environment of space. Traditional fuel gauges rely on gravity to settle liquids, but spacecraft must use pressure measurements, thermal analysis, and even acoustic sounding to estimate propellant reserves. These measurements become increasingly important as missions progress, with fuel conservation strategies determining how long spacecraft can continue active operations before entering passive monitoring modes. The command and data handling systems aboard spacecraft process information flows that would overwhelm most terrestrial computer networks. Scientific data streams, engineering telemetry, and operational commands all flow through these electronic nervous systems simultaneously, with priority scheduling ensuring that critical functions receive necessary resources. Data compression algorithms work continuously to reduce transmission requirements, while error correction systems ensure that information survives the journey to Earth intact, despite noise and interference in the deep space communication environment. Thruster-attitude control systems provide spacecraft pointing accuracy that exceeds the precision of the steadiest human hand, maintaining orientation stability measured in thousandths of degrees. These systems compensate for the subtle torques created by solar radiation pressure, outgassing from heated surfaces, and gravitational gradient effects that tend to disturb spacecraft alignment. The fuel consumption for attitude control is carefully budgeted throughout mission lifetimes, with algorithms optimizing thruster firing patterns to minimize propellant usage while maintaining pointing requirements. The life detection instruments carried by astrobiology missions represent humanity's most sophisticated attempts to identify signs of life beyond Earth. These devices can detect organic molecules at concentration levels that approach the theoretical limits of measurement, while microscopic imaging systems can resolve features smaller than individual bacterial cells. Contamination control for these instruments requires protocols more stringent than medical device manufacturing, ensuring that any life signatures detected represent indigenous biology rather than terrestrial contamination. Radiation hardening techniques protect spacecraft electronics from the high-energy particles that pervade the space environment. Component selection favors designs that can tolerate radiation doses that would be lethal to humans, while circuit redundancy allows systems to continue operating even when individual components are damaged. Some spacecraft carry radiation monitoring systems that track cumulative exposure and predict when critical components might begin to degrade, enabling mission planners to adjust operations to maximize scientific return. The autonomous navigation systems aboard interplanetary spacecraft combine multiple measurement techniques to determine position and velocity with extraordinary precision. Radio ranging from Earth provides basic trajectory information, while optical navigation uses images of destination bodies to refine approach trajectories. Inertial measurement systems track every acceleration and rotation, integrating these measurements over time to maintain continuous knowledge of spacecraft motion even during communication blackouts. Thermal modeling software predicts spacecraft temperatures throughout entire mission timelines, accounting for changing solar distances, planetary shadows, and internal heat generation from electronic systems. These models guide the design of thermal control systems and help mission planners avoid temperature extremes that could damage sensitive components. Real-time thermal monitoring during flight validates these models and enables adjustments to operational procedures when actual conditions differ from predictions. The scientific data archives created by spacecraft missions preserve measurements and observations for future analysis by researchers who may not even be born when the data was collected. These digital libraries contain petabytes of information about planets, moons, asteroids, and the interplanetary medium, organized and catalogued for easy access by the global scientific community. The data formats and storage systems are designed for longevity, ensuring that discoveries made decades ago remain accessible to future generations of researchers. Emergency response procedures for spacecraft operations account for failures that could occur millions of miles from Earth with no possibility of immediate human intervention. Automated safe modes protect critical systems when anomalies are detected, while diagnostic routines help ground controllers understand problems through analysis of telemetry data. Contingency plans exist for virtually every conceivable failure mode, with backup procedures that allow missions to continue even after major system malfunctions. The propulsion efficiency achieved by ion drives and other electric propulsion systems enables missions that would be impossible with conventional chemical rockets. These systems accelerate propellant to velocities 10 times higher than chemical exhaust, providing fuel efficiency that allows spacecraft to visit multiple destinations during single missions. The gentle but persistent thrust from electric propulsion can accelerate spacecraft to higher velocities than conventional systems, while using only a fraction of the propellant mass. Instrument calibration systems ensure that scientific measurements remain accurate throughout multi-year missions, despite the gradual degradation that affects all electronic components exposed to the space environment. Built-in calibration sources provide known reference signals that allow instrument responses to be tracked over time, while periodic observations of standard targets enable comparisons with ground-based measurements. These calibration procedures often consume significant portions of mission time, but are essential for maintaining data quality. The mechanical systems aboard spacecraft operate without lubrication in the vacuum environment of space, relying on dry lubricants and specialized bearing materials that function reliably for years without maintenance. Moving parts are minimized in spacecraft design, but where motion is necessary, the mechanisms must operate flawlessly despite temperature cycling, radiation exposure, and the absence of atmospheric pressure. Testing these systems requires vacuum chambers that simulate space conditions throughout the expected operational lifetime. Communication relay systems enable spacecraft missions that would otherwise be impossible due to line-of-sight limitations or power constraints. Orbiting satellites can relay signals from surface rovers to Earth, while spacecraft positioned at gravitational balance points provide continuous communication links for missions on the far side of celestial bodies. These relay networks extend the reach of space exploration by overcoming the communication challenges that would otherwise limit mission operations. The software verification processes for spacecraft control systems involve testing that exceeds the rigor applied to any other type of programming. Every line of code is analyzed for potential failure modes, while simulation testing exercises spacecraft software through millions of operational scenarios. Formal verification techniques prove mathematically that critical software functions will operate correctly under all possible conditions, providing confidence levels that approach absolute certainty. Spacecraft trajectory optimization algorithms solve complex mathematical problems that balance fuel consumption, flight time, and scientific objectives to determine optimal flight paths through the solar system. These calculations account for the gravitational influences of all major bodies, the changing positions of planets over multi-year timescales, and the operational constraints of spacecraft systems. The resulting trajectories often involve multiple gravitational assists and course corrections that guide spacecraft to their destinations with minimal fuel consumption. Power system redundancy ensures that spacecraft can continue operating even after the failure of primary electrical generation or distribution components. Multiple solar panel strings can be isolated if individual panels are damaged, while battery systems include redundant cells and charging circuits. Load shedding algorithms automatically reduce power consumption during emergencies, prioritizing critical systems while disabling non-essential functions to extend operational lifetime. The atmospheric monitoring instruments aboard planetary missions measure trace gases that provide insights into geological processes, weather patterns, and potential biological activity. These spectrometers can detect molecular species at concentration levels of parts per trillion, while temporal monitoring reveals seasonal variations and long-term trends. The data collected by these instruments contributes to climate models and atmospheric chemistry studies that enhance our understanding of planetary evolution. Spacecraft system integration testing verifies that all subsystems work together harmoniously despite the complexity of modern space missions. Interface compatibility between different components is verified through extensive testing, while timing analyses ensure that data flows and control signals arrive at their destinations within required windows. These integration tests often reveal subtle interactions between systems that would be impossible to predict through analysis alone. The debris shielding systems that protect spacecraft from micrometeorite impacts use multiple layers of specialized materials designed to break up incoming particles and absorb their kinetic energy. Whipple shields use spaced layers that cause projectiles to fragment and spread their impact energy over larger areas, while stuffed shields include intermediate layers of fabric or foam that further dissipate particle energy. These protection systems add mass to spacecraft but are essential for missions that will operate for years in the debris-rich environment of interplanetary space. Navigation accuracy requirements for spacecraft missions often demand position knowledge to within a few meters, despite distances of millions of miles from Earth. Radio ranging measurements combined with Doppler tracking provide the basic trajectory information, while precise timing systems enable these measurements to achieve the required accuracy. The mathematics of orbit determination combine multiple observation types through complex filtering algorithms that estimate spacecraft states with remarkable precision. As these mechanical wanderers continue their eternal journeys through the cosmic darkness, they carry within their electronic memories not just scientific data and engineering telemetry, but the accumulated hopes and dreams of countless individuals who dedicated their careers to expanding human knowledge. Each successful transmission brings new understanding of worlds that exist beyond our direct experience, while every operational milestone represents a triumph of human ingenuity over the challenges of distance, time, and the hostile environment of space. The quiet persistence of these vessels as they drift through interplanetary space reminds us that exploration itself is perhaps humanity's most noble endeavor, driving us to reach beyond the comfortable familiarity of our homeworld in search of answers to questions that have puzzled our species since we first looked up at the stars. In their patient orbits and distant trajectories, spacecraft embody our deepest curiosity about the universe and our place within it, mechanical ambassadors carrying Earth's greeting to whatever wonders await discovery in the vast ocean of space. Their electronic sensors continue gathering data while we sleep, their radio transmitters faithfully carrying whispers of discovery across the billions of miles that separate them from home. In the gentle hum of their systems and the patient precision of their movements, we find a technological poetry that speaks to something fundamental about the human spirit, our irrepressible need to explore, to understand, and to reach toward the infinite mystery that surrounds our small blue world, drifting in the cosmic dark. The software that governs spacecraft operations represents programming artistry at its most demanding, where every line of code must function flawlessly for decades without updates or patches. These digital instructions operate in an environment where a single bit flip caused by cosmic radiation could potentially end a billion-dollar mission. The programmers who craft this code work with a patience that mirrors the spacecraft themselves, testing each algorithm through millions of simulated scenarios before trusting it to make autonomous decisions in the depths of space. Error correction algorithms work silently within spacecraft computers, constantly checking and double-checking stored information to detect when high-energy particles have altered critical data. These digital guardians can reconstruct corrupted information from redundant copies, ensuring that navigation data, scientific measurements, and operational parameters remain intact despite the radiation bombardment that would quickly destroy unprotected electronics. The elegance lies in their invisibility, performing essential maintenance without human awareness or intervention. Spacecraft computers often carry 3 identical processing units that vote on every decision, a democratic approach to computation where majority rule prevents single failures from compromising mission success. When radiation damages one computer, the other 2 continue operating normally while automatically isolating the faulty unit. This triple redundancy extends beyond processors to memory systems, communication links, and even the software itself, creating layers of protection that have allowed some missions to operate for decades beyond their planned lifetimes. The scheduling algorithms aboard spacecraft orchestrate complex sequences of activities with temporal precision that rivals the most sophisticated Earthbound systems. These digital conductors must balance competing demands for limited resources, ensuring that scientific observations occur at precisely the right moments while maintaining adequate power reserves and data storage capacity. They account for the changing geometry of planetary orbits, the degradation of solar panel output over time, and the communication windows when Earth-based antennas can receive precious data streams. Fault detection systems monitor thousands of spacecraft parameters continuously, learning to recognize subtle patterns that might indicate developing problems before they become critical. These artificial diagnosticians track temperature trends, voltage fluctuations, and mechanical vibrations with sensitivity that exceeds human perception. When anomalies are detected, automated responses can switch to backup systems, adjust operational modes, or place the spacecraft in protective configurations while awaiting detailed analysis from ground controllers. The memory systems aboard deep space explorers preserve scientific discoveries and operational data through storage technologies that must function reliably in temperature extremes that would destroy conventional computer components. Solid-state memory chips undergo extensive radiation testing and thermal cycling to ensure they can maintain data integrity for decades of operation. Multiple copies of critical information are distributed across separate storage systems, with error detection codes that can reconstruct damaged data from partial fragments. Autonomous decision-making capabilities enable spacecraft to respond to unexpected situations without waiting for instructions that might take hours to arrive from Earth. These artificial intelligence systems can recognize equipment malfunctions, adjust scientific observations based on changing conditions, and even modify flight trajectories to avoid newly discovered hazards. The sophistication of these systems continues evolving throughout mission lifetimes, with machine learning algorithms that improve performance based on operational experience. Power management systems aboard spacecraft function like electronic nervous systems, continuously monitoring and adjusting energy distribution to meet the varying demands of different subsystems. Solar panel output fluctuates with distance from the Sun and degradation over time, while battery storage capacity gradually diminishes through countless charge cycles. These systems must maintain stable electrical conditions despite these changing parameters, ensuring that critical functions continue operating even during periods of reduced power generation. The communication systems that maintain contact with distant spacecraft represent miracles of electronic sensitivity, detecting radio signals so weak they carry less energy than a snowflake falling on the antenna. These receivers must distinguish meaningful data from cosmic background noise, extracting scientific discoveries and engineering telemetry from transmissions that have traveled billions of miles through interplanetary space. The mathematics of signal processing enable these systems to reconstruct perfect digital information from signals that appear indistinguishable from random static. Data compression algorithms work continuously aboard spacecraft, transforming raw scientific measurements into efficient digital packages that maximize the scientific value transmitted during limited communication windows. High-resolution images that would fill entire computer hard drives are reduced to streams of numbers that preserve every essential detail while eliminating redundant information. These compression systems must operate flawlessly for years, making split-second decisions about information priority without human oversight. The guidance systems that navigate spacecraft through interplanetary space combine multiple measurement techniques with mathematical precision that enables arrivals at distant destinations within windows measured in minutes after journeys lasting years. Star trackers photograph celestial landmarks and compare their images to onboard catalogues containing the positions of thousands of reference stars. Inertial measurement units sense every acceleration and rotation, integrating these measurements continuously to maintain knowledge of spacecraft motion, even during communication blackouts. Attitude control systems maintain spacecraft orientation with stability that exceeds the steadiest human hand, using reaction wheels that spin silently within the vehicle to create gyroscopic forces for precise pointing adjustments. These mechanical gyroscopes can orient multi-ton spacecraft with movements measured in thousandths of degrees, enabling scientific instruments to track distant targets with extraordinary accuracy. When the wheels reach their speed limits, small thrusters fire brief gas pulses to desaturate the system while maintaining perfect pointing control. Thermal regulation systems create carefully controlled temperature environments within spacecraft, despite the extreme conditions of space, where surfaces facing the Sun can reach temperatures hot enough to melt lead, while those in shadow experience cold, more severe than Antarctic winter. Heaters warm critical components during long planetary shadow transits, while radiators dissipate excess heat generated by electronic systems and scientific instruments. Multi-layer insulation blankets wrap sensitive equipment like cosmic quilts, their reflective surfaces bouncing thermal radiation while trapping essential warmth within. The propulsion systems that guide spacecraft through the solar system must remain dormant for months or years between critical maneuvers, yet ignite reliably when commanded to perform course corrections or orbital insertions. These rocket engines operate in vacuum conditions that would challenge any terrestrial machinery, their components subjected to temperature cycling and radiation exposure that would quickly destroy conventional equipment. The engineering challenge of creating systems that can sit unused for extended periods and then function perfectly on demand requires materials and designs that far exceed Earthbound standards. Scientific instrument suites aboard robotic explorers extend human senses across impossible distances, detecting phenomena that no Earth-based observer could ever experience directly. Spectrometers analyze the chemical composition of alien atmospheres by examining absorbed wavelengths in reflected sunlight, revealing the presence of water vapor, methane, and other molecules that tell stories of distant worlds. Magnetometers map invisible magnetic fields that shape planetary environments, while particle detectors count atomic fragments streaming through space at nearly the speed of light. The mechanical deployment systems aboard spacecraft unfold like technological origami, transforming compact launch configurations into full operational geometry through sequences of precisely choreographed movements. Solar panel arrays extend to sizes that dwarf the central spacecraft, while antenna reflectors bloom into parabolic surfaces that can focus radio signals across interplanetary distances. These deployment mechanisms must function flawlessly after months of dormancy, their springs and actuators operating reliably despite exposure to temperature extremes and the vacuum of space. Contamination control protocols ensure that spacecraft exploring potentially habitable worlds maintain biological cleanliness standards more stringent than hospital operating rooms. Every component undergoes sterilization procedures that would eliminate any terrestrial microorganisms, while assembly occurs in clean rooms where even the air is filtered to remove particles smaller than bacteria. These planetary protection measures require complete documentation of biological burden throughout the manufacturing process, ensuring that any life signatures detected represent indigenous biology rather than earthly contamination. The optical systems aboard space telescopes achieve image quality that surpasses ground-based observatories despite operating in the harsh environment beyond Earth's protective atmosphere. Mirror surfaces maintain their precision geometry through temperature cycling that would warp terrestrial optics, while pointing systems track celestial targets with stability measured in milliseconds. These space-based observatories can observe single targets for extended periods without atmospheric interference, accumulating photons from sources so distant their light began its journey when the universe was young. Sample collection mechanisms on planetary explorers represent some of the most sophisticated remote manipulation ever achieved, extending robotic arms across alien landscapes with movements planned months in advance to account for communication delays. Drilling systems bore into rock formations that have remained undisturbed for geological ages, extracting cores that preserve the history of distant worlds within their crystalline structures. These samples undergo analysis through miniaturized laboratories that rival major research facilities in their analytical capabilities, all contained within packages no larger than briefcases. Cryogenic cooling systems maintain scientific instruments at temperatures approaching absolute zero, creating pockets of extreme cold that enable measurements impossible under normal conditions. Liquid helium dewars preserve their precious contents for years through thermal isolation techniques that far exceed any terrestrial refrigeration technology. The gradual warming of these systems often determines mission lifetimes, as instruments requiring ultra-low temperatures cease operations when cryogenic supplies are finally exhausted. The precision timing systems that coordinate spacecraft operations rely on atomic clocks that maintain accuracy despite the relativistic effects of high-speed travel through varying gravitational fields. These timepieces synchronize observations across multiple spacecraft separated by thousands of miles, enabling interferometric measurements that combine data from widely distributed vehicles. Time itself becomes a scientific instrument with nanosecond precision, enabling ranging measurements that determine spacecraft positions to within meters across interplanetary distances. Radiation shielding systems protect sensitive electronics from high-energy particles that would quickly destroy unprotected components. Specialized materials absorb or deflect cosmic rays and solar wind particles, while circuit designs incorporate redundancy that allows systems to continue functioning even when individual components are damaged. Some spacecraft generate artificial magnetic fields that create protective bubbles around critical systems, mimicking the magnetosphere that shields Earth from space radiation. The atmospheric entry systems that guide spacecraft through planetary atmospheres must function perfectly during brief, violent transitions from interplanetary space to surface operations. Heat shields endure temperatures that exceed the melting point of most materials. Their ablative surfaces designed to carry away thermal energy through controlled erosion. Parachute systems deploy in carefully timed sequences, their operation calculated to achieve gentle touchdowns, despite atmospheric conditions that may differ significantly from pre-mission models. Life support systems aboard crewed spacecraft create self-contained biospheres that recycle air, water, and waste with efficiency that approaches natural ecosystems. Atmospheric processes maintain perfect balances of oxygen and nitrogen while removing carbon dioxide and trace contaminants that could become toxic in the closed environment of a spacecraft. Water recovery systems purify all available moisture, including that reclaimed from crew waste, producing drinking water that often exceeds the quality of municipal supplies on Earth. The robotic systems that maintain spacecraft operations work with mechanical precision that never tires or loses focus, performing thousands of small adjustments and maintenance tasks without human intervention. Automated mechanisms deploy covers to protect instruments from dust storms, adjust solar panel angles to track the sun, and even repair minor system malfunctions through pre-programmed sequences. These robotic caretakers extend mission lifetimes by preventing the accumulation of small problems that could cascade into major failures. Deep space communication networks span the globe to ensure continuous contact with distant explorers as Earth rotates on its axis. Massive dish antennas track spacecraft across the sky with mechanical precision, their pointing systems compensating for the planet's rotation while maintaining perfect alignment with targets billions of miles away. The sensitivity of these receivers approaches theoretical limits, amplifying whispers from the cosmic dark until they can be decoded into scientific data and engineering telemetry. Spacecraft trajectory optimization involves solving mathematical problems of extraordinary complexity, balancing fuel consumption against flight time while accounting for the gravitational influences of every major body in the solar system. These calculations must predict planetary positions years into the future, threading spacecraft through gravitational keyholes that exist for only brief windows. The resulting flight paths often involve multiple gravitational assists that use planetary motion to accelerate spacecraft to destinations that would otherwise require impossible amounts of propellant. The manufacturing processes for spacecraft components involve quality control procedures that exceed those found in any other industry, with every part traceable back to its original materials and production methods. Clean room assembly prevents contamination that could compromise sensitive instruments, while testing protocols subject components to conditions more severe than they will encounter during actual missions. Documentation requirements create complete pedigrees for every component, enabling detailed failure analysis if problems occur years later. Emergency response procedures for spacecraft operations account for failures that could occur millions of miles from Earth with no possibility of immediate human assistance. Automated safe modes protect critical systems when anomalies are detected, while diagnostic routines help ground controllers understand problems through analysis of telemetry streams. Contingency plans exist for virtually every conceivable failure scenario, with backup procedures that enable missions to continue even after major system malfunctions. The scientific data archives created by spacecraft missions preserve observations and measurements for analysis by researchers who may not be born when the data was originally collected. These digital libraries contain vast quantities of information about planets, moons, asteroids, and the interplanetary environment, organized and indexed for access by the global scientific community. Storage formats are designed for longevity, ensuring that discoveries made decades ago remain available to future generations of investigators. International cooperation enables spacecraft missions that transcend political boundaries, bringing together scientists and engineers from dozens of countries in pursuit of common goals. These partnerships demonstrate humanity's ability to work together toward objectives that no single nation could achieve alone, pooling resources and expertise to push the boundaries of human knowledge ever further into the cosmic unknown. As these mechanical explorers continue their patient journeys through the interplanetary night, they embody our species' deepest curiosity about the universe and our place within its vast expanse. Each transmission carries new discoveries across impossible distances, while every successful operation represents a triumph of human ingenuity over the challenges of space exploration. In their quiet orbits and distant trajectories, spacecraft remind us that the desire to explore and understand may be our most defining characteristic, driving us to reach beyond the comfortable boundaries of our world in search of answers to questions that have intrigued humanity since we first gazed upward at the star-filled sky. The electronic heartbeats of these vessels pulse steadily through the cosmic silence, their systems humming with the quiet confidence of machines designed to operate far beyond human reach. In contemplating their remarkable achievements, we find ourselves drawn into the same sense of wonder that originally inspired their creation, that fundamental human drive to explore, to discover, and to understand the infinite mystery that surrounds our small world, drifting peacefully through the vast ocean of space. The quiet precision of spacecraft docking operations unfolds like a mechanical ballet performed at impossible velocities, where supply vessels approach their orbital destinations with movements measured in millimeters per second. These approaching craft must match not only the speed of their targets, but also their exact trajectory through three-dimensional space, closing the final distance with such delicacy that the slightest miscalculation could result in catastrophic collision. The robotic arms that guide these rendezvous extend with movements more graceful than any human gesture, their mechanical joints articulating with precision that masks the extraordinary complexity of operating at 17,000 miles per hour. Advanced life detection systems aboard astrobiology missions carry instruments capable of identifying organic molecules at concentrations that approach the theoretical limits of measurement. These devices can distinguish between the chemical signatures of living processes and the random molecular patterns created by geological activity, searching for the subtle imbalances that might indicate biological activity on distant worlds. Sample analysis chambers no larger than lunchboxes contain spectrometers, microscopes, and chemical laboratories that rival major research institutions in their analytical capabilities, all designed to function reliably in temperature extremes that would destroy conventional scientific equipment. The magnetic field mapping systems aboard planetary explorers trace invisible lines of force that shape entire worlds, detecting field strengths and orientations that reveal the internal structure of planets and moons. These magnetometers can sense fields millions of times weaker than Earth's magnetic environment, mapping the complex interactions between solar wind particles and planetary magnetospheres. The data they collect helps scientists understand how magnetic shields protect atmospheric envelopes from erosion by charged particles streaming from distant stars. Information crucial for assessing the habitability of worlds orbiting other suns. Atmospheric composition analyzers aboard entry probes measure trace gases during their brief plunges through alien atmospheres, collecting data during descents that last only minutes, but provide insights into chemical processes occurring over geological timescales. These instruments must operate while experiencing deceleration forces that would crush human bodies, their sampling systems functioning reliably despite temperatures and pressures that fluctuate wildly during atmospheric entry. The molecular signatures they detect tell stories of volcanic outgassing, photochemical reactions, and possibly even biological metabolism occurring in atmospheres we may never visit directly. Dust devil monitoring systems on planetary landers track the miniature tornadoes that dance across Martian plains, measuring wind speeds and particle concentrations within these ephemeral phenomena. These weather stations operate continuously for years, their sensors exposed to temperature swings that range from tropical warmth to Arctic cold within single Martian days. The atmospheric data they collect contributes to climate models that help scientists understand how dust storms can engulf entire planets, information essential for planning future human expeditions to these distant worlds. The seismic monitoring equipment deployed by planetary landers listens for the subtle tremors that reveal the internal structure of alien worlds, detecting Marsquakes and moonquakes with sensitivity that exceeds terrestrial earthquake detection systems. These instruments must distinguish between genuine seismic events and the thermal creaking of their own mechanical components as temperature cycles stress metal and composite structures. The seismic waves they detect travel through planetary interiors that have remained hidden since the formation of the solar system, carrying information about core composition and geological processes that shaped worlds billions of years ago. Radiation monitoring systems aboard spacecraft track the invisible particles that stream through interplanetary space, measuring cosmic ray intensities and solar wind variations that create the space weather affecting all electronic systems beyond Earth's protective magnetosphere. These detectors can identify individual atomic nuclei traveling at significant fractions of light speed, analyzing their energy and composition to understand the violent stellar processes that accelerate them to such incredible velocities. The data they collect helps mission planners predict radiation hazards that could affect future crewed expeditions to Mars and beyond. Surface composition analyzers use laser spectroscopy to vaporize tiny portions of rocks and soil, creating plasma clouds whose light reveals the elemental makeup of alien geology. These systems can identify trace elements present in concentrations of parts per million, detecting the chemical signatures of water interaction, volcanic activity, and sedimentary processes that occurred in ancient epochs. The precision of these measurements enables scientists to reconstruct environmental conditions that existed when the solar system was young and planets were still forming their current characteristics. Subsurface radar systems peer beneath planetary surfaces, using radio waves that penetrate soil and rock to reveal buried structures invisible to optical instruments. These ground-penetrating radar systems can map underground water ice, ancient riverbeds, and geological layers that preserve the history of climate changes spanning millions of years. The electromagnetic pulses they transmit and receive provide three-dimensional images of subsurface features, revealing hidden landscapes that tell stories of warmer, wetter periods when conditions might have been suitable for life. Ice drilling systems extract cores from frozen deposits that preserve atmospheric samples from ancient eras, creating libraries of climate history stored in crystalline form. These robotic drilling platforms must operate in temperatures cold enough to freeze carbon dioxide, their heating systems preventing the formation of ice that could jam mechanical components. The samples they collect contain bubbles of ancient atmosphere and dust particles that settled from prehistoric skies, providing direct evidence of environmental conditions that existed before Earth developed complex life forms. Gravity measurement systems detect tiny variations in planetary gravitational fields that reveal the distribution of mass within celestial bodies, mapping the locations of dense metallic cores, subsurface oceans, and hollow lava tubes. These instruments achieve measurement precision that exceeds 1 part in a billion, detecting gravitational anomalies that would be imperceptible to human senses. The gravitational maps they create help scientists understand the internal structure of worlds where direct exploration remains impossible, revealing whether moons harbour liquid water oceans beneath their frozen surfaces. Sample caching systems preserve collected specimens in sealed containers, designed to maintain their pristine condition for years until future missions can retrieve them for return to Earth. These storage systems must protect samples from cosmic radiation, temperature cycling, and contamination while maintaining precise environmental conditions that preserve chemical and biological signatures. The caching technology represents a bridge between current robotic exploration and future sample return missions that will bring pieces of other worlds back to terrestrial laboratories for detailed analysis. Real-time image processing systems aboard spacecraft enhance and analyze photographs as they are captured, identifying interesting features that merit additional observation while communication windows remain open. These artificial intelligence systems can recognize geological formations, atmospheric phenomena, and surface changes that might indicate active processes occurring on distant worlds. The automated analysis capabilities enable spacecraft to make autonomous decisions about follow-up observations, maximizing scientific return when communication delays prevent real-time human oversight. Precision landing systems guide spacecraft to touchdown sites selected for their scientific value, navigating between boulders and craters to reach locations that offer the best opportunities for discovery. These guidance systems combine radar altimetry, optical navigation, and hazard avoidance algorithms that function autonomously during the critical final moments of descent. The accuracy they achieve allows landers to touch down within walking distance of previously identified targets, enabling detailed investigation of features that caught scientists' attention in orbital surveys conducted years earlier. Atmospheric parachute systems must deploy reliably in atmospheres with densities and compositions that differ dramatically from Earth conditions, their fabric and rigging materials selected to withstand temperature extremes and chemical environments that would quickly destroy conventional materials. These systems often represent the only means of achieving gentle touchdowns on worlds with substantial atmospheres, their performance determining whether expensive scientific payloads survive to conduct their intended investigations. The engineering challenge of creating parachutes that function in alien atmospheres requires extensive testing in specialized facilities that simulate extraterrestrial conditions. Long-range mobility systems enable rovers to traverse distances measured in miles across planetary surfaces that have never felt the tread of wheels or tracks. These vehicles must navigate terrain that ranges from sandy plains to rocky outcrops, their suspension systems designed to maintain stability while climbing slopes and traversing obstacles that would challenge any terrestrial vehicle. The autonomous navigation algorithms that guide these rovers can plan routes around hazards and towards scientifically interesting targets, enabling exploration of vast areas during missions that span multiple Earth years. Microscopic imaging systems reveal details of alien materials at magnifications that approach the resolution of terrestrial laboratory instruments, capturing images of individual mineral grains and possible microfossils preserved in ancient rock formations. These optical systems must maintain perfect focus despite temperature fluctuations and mechanical vibrations that would blur conventional microscopes, their electronic sensors protected from radiation damage that could degrade image quality over time. The photographs they transmit to Earth provide the closest possible examination of extraterrestrial materials until actual samples can be returned for laboratory analysis. Chemical laboratory systems conduct sophisticated analyses using techniques that parallel those employed in major research institutions, identifying molecular compounds and isotopic ratios that reveal the formation history of planetary materials. These miniaturized laboratories contain reagents and analytical instruments that must remain stable and functional for years in the harsh space environment. Their results providing chemical fingerprints that help scientists understand the processes that shape the solar system. The precision of these analyses enables researchers to distinguish between materials formed in different environments and to identify signatures that might indicate past or present biological activity. Sample preparation systems process collected materials through grinding, sieving, and chemical treatment procedures that prepare specimens for detailed analysis by onboard instruments. These automated systems must handle samples with contamination control protocols that prevent cross-contamination between different collection sites, while maintaining the pristine condition necessary for meaningful scientific results. The mechanical precision required for these operations challenges engineers to create systems that can manipulate materials measured in milligrams while operating in vacuum conditions and temperature extremes. Environmental monitoring systems track atmospheric conditions, surface temperatures, and radiation levels continuously throughout mission lifetimes, creating comprehensive databases of environmental conditions on alien worlds. These weather stations must function reliably through seasonal changes that may last for Earth months, their sensors calibrated to maintain accuracy despite gradual degradation caused by dust accumulation and radiation exposure. The environmental data they collect provides context for all other scientific observations, helping researchers understand how changing conditions affect geological processes and potential biological activity. Power generation systems must provide reliable electricity throughout mission lifetimes that often extend far beyond original specifications, their solar panels or nuclear generators maintaining adequate output despite gradual degradation and environmental challenges. Solar arrays must continue generating power while accumulating dust that reduces their efficiency, while radioisotope generators must provide steady output as their radioactive fuel slowly decays according to physical laws that cannot be altered. The electrical power these systems provide determines mission capabilities and lifetimes, making power generation one of the most critical aspects of spacecraft design. Data transmission systems compress scientific observations and engineering telemetry into efficient digital formats that can survive transmission across interplanetary distances despite noise and interference that would overwhelm conventional communication systems. These transmission protocols must maximize information content while minimizing bandwidth requirements, enabling spacecraft to relay their discoveries to Earth during communication windows that may last only hours each day. The error correction algorithms embedded in these systems can reconstruct perfect data from transmissions that arrive corrupted by cosmic interference. As these mechanical ambassadors continue their patient work across the solar system, they extend human presence to worlds that remain beyond our direct reach, their instruments serving as our eyes, ears, and hands in environments where no human could survive unprotected. Each successful observation represents a small victory over the vast distances and hostile conditions that separate us from other worlds, while every data transmission carries new understanding across the cosmic gulf that surrounds our home planet. The quiet dedication of these robotic explorers mirrors the persistence of the scientists and engineers who created them, individuals who devoted careers to extending human knowledge beyond the comfortable boundaries of Earth. In their electronic vigilance and mechanical precision, spacecraft embody our species' greatest aspirations, carrying our curiosity and wonder to distant realms where they continue the ancient human tradition of exploration and discovery. Their sensors continue gathering data while we rest, their transmitters faithfully carrying whispers of revelation across billions of miles of empty space. In the gentle precision of their movements and the patient accumulation of their observations, we find a technological poetry that speaks to something fundamental about human nature, our irrepressible need to explore, to understand, and to reach toward the infinite mystery that beckons from beyond the edge of our small world, drifting in the cosmic dark. The software verification processes that govern spacecraft autonomy involve testing procedures more rigorous than any other form of programming. where every possible scenario must be anticipated, and every line of code proven mathematically sound. These digital instruction sets operate in isolation for years at a time, making countless decisions without human oversight, while carrying the accumulated wisdom of thousands of programmers who will never see their creations in operation. The elegance of these systems lies in their invisible competence, managing complex spacecraft functions so seamlessly that their sophisticated decision-making remains hidden beneath layers of automated routine. Magnetic attitude control systems create invisible forces that orient spacecraft using the fundamental properties of planetary magnetic fields, their electromagnetic coils generating precisely calculated magnetic moments that interact with natural field lines to produce gentle torques. These systems consume minimal power while providing attitude control that functions indefinitely without propellant. Their operations so subtle that spacecraft appear to drift naturally into proper alignment. The mathematics governing these interactions account for the three-dimensional complexity of planetary magnetospheres, enabling spacecraft to maintain pointing accuracy through purely electromagnetic forces. Interplanetary dust particle counters detect microscopic fragments traveling through space at velocities that would vaporize larger objects, measuring impact rates and particle sizes that reveal the distribution of debris throughout the solar system. These sensors can register collisions with particles smaller than bacteria. Their detection systems so sensitive they can distinguish between meteoritic dust and material ejected from planetary surfaces by impact events. The data they collect helps mission planners understand collision hazards and provides insights into the processes that created the debris fields surrounding planets and asteroids. Orbital mechanics software calculates spacecraft trajectories with precision that accounts for gravitational perturbations from bodies as distant as the outer planets, their algorithms integrating forces so subtle they would be imperceptible over short timescales, but become significant during multi-year missions. These computational systems must predict planetary positions years into the future, while accounting for relativistic effects that become important when dealing with precision navigation across vast distances. The mathematical elegance of these calculations transforms the chaotic complexity of multi-body gravitational systems into predictable flight paths that thread through the solar system with extraordinary accuracy. Plasma wave detectors measure electromagnetic fluctuations in the charged particle environment surrounding spacecraft, sensing radio emissions generated by magnetic field interactions and particle acceleration processes occurring in planetary magnetospheres. These instruments can detect signals so faint they would be overwhelmed by terrestrial radio interference. Their receivers tune to frequencies that reveal the invisible electromagnetic weather pervading interplanetary space. The wave patterns they measure tell stories of solar-wind interactions, auroral processes, and the complex physics governing the boundary regions where planetary magnetic fields meet the interstellar medium. Sample containment systems preserve collected materials in environments more sterile than surgical operating theaters, their sealed chambers maintaining atmospheric compositions and temperature conditions that prevent contamination or chemical alteration of precious specimens. These storage systems must function reliably for years and the protecting samples from cosmic radiation, temperature cycling vacuum of space, their sealing mechanisms designed to maintain integrity despite the thermal stresses that would compromise conventional containers. The preservation techniques they employ ensure that chemical and isotopic signatures remain unaltered until samples can be analyzed by instruments on Earth or by future missions. Autonomous hazard avoidance systems guide spacecraft through asteroid fields and planetary ring systems using real-time image processing that identifies potential collision threats and calculates avoidance maneuvers within seconds. These systems combine optical sensors with sophisticated algorithms that can distinguish between harmless dust and dangerous debris. Their decision-making capabilities enabling spacecraft to navigate safely through environments where human reaction times would be inadequate. The split-second timing required for these operations demonstrates the remarkable capability of modern spacecraft to protect themselves while continuing their scientific missions. Thermal vacuum testing subjects spacecraft to environmental conditions more severe than anything they will encounter during actual missions, cycling temperatures between extremes that would shatter conventional materials while maintaining vacuum levels that exceed the emptiness of interstellar space. These testing procedures can last for months, with spacecraft operating continuously while engineers monitor every system for signs of degradation or failure. The endurance required for these tests often exceeds the patience of their human operators, yet the confidence gained from successful completion justifies the enormous investment in time and resources. Multispectral imaging systems capture photographs in waveform, revealing surface lengths invisible to human vision compositions and atmospheric phenomena that remain hidden in conventional photography. These cameras can distinguish between different types of rock, ice, and atmospheric gases based on their unique spectral signatures, creating false color images that highlight features of scientific interest. The processing algorithms that convert raw spectral data into meaningful images operate automatically aboard spacecraft, making real-time decisions about image enhancement and compression that maximize scientific content while minimizing transmission requirements. Precision pointing systems maintain spacecraft orientation with stability that exceeds the steadiest telescope mount, their control algorithms compensating for disturbances so subtle they would be imperceptible to human senses, yet significant enough to blur scientific observations. These systems must account for solar radiation pressure, thermal expansion effects, and the microscopic forces created by outgassing materials, their corrections measured in thousandths of degrees. The mechanical precision they achieve enables scientific instruments to track distant targets for extended periods, accumulating observations that would be impossible without such extraordinary pointing stability. Deep space navigation beacons provide reference points for spacecraft positioning using pulsars whose radio emissions arrive with clockwork regularity despite their origins thousands of light years from the solar system. These natural lighthouses enable navigation techniques that function independently of Earth-based tracking systems, their signals carrying timing information precise enough to determine spacecraft positions to within a few kilometers across interplanetary distances. The technology required to use pulsar navigation pushes radio astronomy techniques to their limits, detecting signals so faint they require enormous antennas and sophisticated signal processing to extract useful timing data. Robotic sample manipulation systems extend human dexterity across interplanetary distances, their mechanical hands capable of grasping, lifting, and manipulating objects with movements choreographed months in advance to account for communication delays. These systems must operate in temperature extremes and vacuum conditions that would quickly destroy conventional robotics, their joints and actuators designed to function reliably after years of dormancy in the space environment. The precision they achieve rivals human manipulation while operating in gravitational fields and atmospheric conditions that differ dramatically from terrestrial environments. Atmospheric composition monitoring systems track trace gases that may indicate geological activity, seasonal changes, or even biological processes occurring in alien atmospheres. These spectrometers can detect molecular species present in concentrations measured in parts per billion, their measurements revealing chemical processes occurring over timescales ranging from hours to geological epochs. The sensitivity required for these observations challenges instrument designers to create systems that can distinguish between different molecular signatures while operating in the harsh radiation environment of space. Cryogenic preservation systems maintain scientific samples and instruments at temperatures approaching absolute zero, using cooling techniques that far exceed terrestrial refrigeration capabilities. These systems can preserve the molecular structure of collected materials for years while consuming minimal electrical power. Their thermal isolation so effective that heat leakage rates are measured in milliwatts. The gradual warming of these systems often determines mission lifetimes, as instruments requiring ultra-low temperatures cease operations when cooling capacity is finally exhausted. Surface-penetrating radar systems peer beneath planetary surfaces using electromagnetic pulses that reveal buried structures invisible to optical observations, mapping subsurface layers that preserve geological history spanning millions of years. These radar systems must distinguish between different types of buried materials based on their electromagnetic properties, their signal processing algorithms capable of creating three-dimensional images of underground features. The penetration depth they achieve varies with surface composition and moisture content, enabling detailed mapping of subsurface ice deposits and buried geological formations. Dust mitigation systems protect sensitive instruments from the microscopic particles that pervade planetary atmospheres and surface environments, using electrostatic fields and mechanical covers that deploy automatically when dust storms threaten critical components. These protection systems must function reliably in environments where dust accumulation could compromise optical surfaces or clog mechanical mechanisms, their operation timed to coincide with seasonal dust storm patterns that may last for months. The materials used in these systems resist the erosive effects of high-velocity dust impacts while maintaining their protective effectiveness throughout extended mission lifetimes. Long-duration hibernation systems place spacecraft in dormant modes that minimize power consumption and component wear during extended cruise phases between active observation periods. These systems can maintain essential functions for years while reducing electrical consumption to levels that barely exceed background power requirements. Their wake-up procedures, designed to restore full operational capability within hours of receiving activation commands. The engineering challenge of creating systems that can remain dormant for extended periods and then function perfectly when needed requires component selection and design approaches that prioritize long-term reliability over peak performance. Precision mass spectrometry systems analyze the atomic composition of collected samples with accuracy that approaches the theoretical limits of measurement, identifying isotopic ratios that reveal the formation history of planetary materials. These instruments can distinguish between atoms that differ by single neutrons, their measurements providing chemical fingerprints that help scientists understand the processes that shaped the solar system billions of years ago. The vacuum systems required for these measurements must maintain pressures lower than interstellar space, while protecting delicate components from contamination that could compromise analytical accuracy. Gravitational wave detection systems aboard some advanced missions attempt to measure the subtle ripples in spacetime created by distant cosmic events, their laser interferometers achieving measurement precision that can detect distance changes smaller than the diameter of atomic nuclei. These systems represent the ultimate challenge in precision measurement, requiring isolation from vibrations and thermal fluctuations that would overwhelm the tiny signals they seek to detect. The technology developed for these applications often finds uses in other precision measurement systems aboard spacecraft, advancing the overall capability of space-based science. Autonomous geological surveys enable robotic explorers to identify and investigate scientifically interesting features without waiting for detailed instructions from Earth. They're artificial intelligence systems trained to recognize formations that merit detailed study. These systems can distinguish between different types of rock formations, identify potential fossil-bearing strata, and even detect unusual mineral compositions that might indicate past water activity. The decision-making algorithms that guide these surveys operate within predefined parameters that ensure safe operations while maximizing scientific return from limited operational time. Magnetic field generation systems aboard some spacecraft create artificial magnetospheres that deflect charged particles and protect sensitive electronics from radiation damage. Their electromagnetic coils powered by carefully managed electrical systems that balance protection benefits against power consumption requirements. These magnetic shields can extend several meters from spacecraft surfaces, creating protective bubbles that mimic the natural magnetospheres surrounding planets like Earth. The field strengths required for effective protection represent significant electrical loads that must be balanced against other mission requirements. Solar wind measurement systems detect and analyze the stream of charged particles flowing from the sun, measuring particle velocities, densities, and magnetic field orientations that vary with solar activity cycles spanning years or decades. These instruments can detect individual protons and electrons traveling at speeds exceeding 1,000,000 miles per hour. Their measurements revealing the complex physics governing stellar atmospheres and the interplanetary medium. The data they collect helps scientists understand space weather phenomena that affect spacecraft operations and could impact future human expeditions to other planets. Environmental adaptation systems enable spacecraft to modify their operations based on changing conditions encountered during extended missions. Their algorithms adjusting power consumption, thermal management, and scientific observation schedules to accommodate seasonal variations and equipment degradation. These systems can recognize when environmental conditions exceed design specifications and automatically implement protective measures that ensure continued operations. The flexibility they provide often enables missions to continue long after their original specifications suggested they should have ended. As these remarkable machines continue their patient exploration of the cosmic frontier, they demonstrate humanity's ability to extend our presence and understanding far beyond the boundaries of our home world. Their quiet competence in the face of impossible distances and hostile environments speaks to the ingenuity of their creators and the deep human drive to explore and understand the universe around us. In their electronic vigilance and mechanical precision, they carry forward the ancient tradition of human exploration, pushing the boundaries of knowledge ever outward into the vast mystery that surrounds our small planet, drifting peacefully through the infinite darkness of space. Each successful observation and every data transmission represents a small victory over the challenges that separate us from other worlds, while their continued operation far from home reminds us that curiosity itself may be our species' most remarkable achievement. In the gentle hum of their systems and the patient accumulation of their discoveries, we find a technological poetry that captures something essential about human nature: our irrepressible need to reach beyond the familiar and touch the infinite wonder that beckons from the cosmic depths. The legacy preservation systems aboard long-duration missions ensure that decades of scientific observations remain accessible to future generations of researchers. Their digital archives organized with metadata that will remain meaningful centuries after the original missions have ended. These electronic libraries contain not just raw measurements, but also the analytical algorithms and calibration data necessary to reinterpret findings as understanding scientific evolves. The storage formats are designed with longevity in mind, using encoding schemes that prioritize data integrity over compression efficiency, ensuring that hard-won discoveries survive the gradual degradation that affects all electronic media over extended periods. Microthruster attitude control systems provide spacecraft orientation adjustments using propellant droplets so small they would be invisible to the naked eye. Their impulse bits, measured in micronewtons, yet precise enough to maintain pointing accuracy over years of continuous operation. These miniature rockets consume propellant at rates slower than water dripping from a leaky faucet. Their efficiency enabling attitude control throughout mission lifetimes that span decades. The valve systems that meter these tiny fuel flows operate with reliability that exceeds any terrestrial application, opening and closing millions of times while maintaining seal integrity in the vacuum of space. Plasma physics instruments aboard outer planet missions measure the charged particle environments surrounding gas giants, detecting electromagnetic phenomena that occur on scales dwarfing any terrestrial equivalent. These sensors can distinguish between different types of plasma waves, magnetic field reconnection events, and particle acceleration processes that shape the space environments around worlds like Jupiter and Saturn. The measurements they collect reveal physics that operates under conditions impossible to replicate in earthbound laboratories, extending human understanding of electromagnetic processes that govern much of the visible universe. Seismic wave propagation studies conducted by planetary landers reveal the internal structure of alien worlds through analysis of tremors that travel through crusts and mantles that formed under conditions vastly different from Earth. These instruments detect vibrations so faint they would be overwhelmed by terrestrial background noise, their sensitivity enabling detection of impacts from meteorites no larger than pebbles striking planetary surfaces thousands of miles away. The seismic data they collect provides three-dimensional maps of planetary interiors, revealing whether worlds harbor liquid cores, subsurface oceans, or geological structures that could support indigenous life forms. Atmospheric entry heat shield systems protect spacecraft during the violent transition from interplanetary space to planetary atmospheres. Their ablative materials, designed to vaporize in controlled patterns that carry away thermal energy while maintaining structural integrity. These thermal protection systems must function perfectly during descents that last only minutes, but experience temperature gradients that would instantly vaporize unprotected materials. The engineering challenge of creating materials that can withstand such extreme conditions while remaining lightweight enough for interplanetary transport pushes materials science to its absolute limits. Radio occultation experiments use spacecraft communication signals to probe planetary atmospheres during orbital passes that carry vehicles behind worlds as viewed from Earth. The signal distortions revealing atmospheric density profiles, temperature structures, and composition variations that remain invisible to direct observation. These measurements require precise tracking of radio signal characteristics as spacecraft disappear behind planetary limbs and emerge from shadow, their signal processing algorithms extracting atmospheric information from subtle frequency shifts and amplitude changes. The technique enables atmospheric profiling with vertical resolution measured in kilometers, providing detailed maps of weather patterns and seasonal variations on worlds throughout the solar system. Particle impact detection systems register collisions with microscopic debris, traveling at velocities that would destroy larger objects. Their sensors so sensitive, they can detect individual dust grains striking spacecraft surfaces at speeds exceeding those of rifle bullets. These impact monitors help scientists understand the distribution of debris throughout interplanetary space, while providing early warning of hazardous particle environments that could threaten mission-critical components. The acoustic signatures of these impacts tell stories of their origins, distinguishing between cometary dust, asteroidal fragments, and material ejected from planetary surfaces by ancient impact events. Subsurface ice-mapping radar systems penetrate frozen ground to depths measured in kilometers, revealing the three-dimensional distribution of water ice deposits that could support future human expeditions or indicate past environmental conditions suitable for life. These ground-penetrating instruments must distinguish between different types of buried materials based on their electromagnetic properties, creating detailed maps of subsurface structure that guide selection of landing sites for future missions. The data they collect often reveals unexpected complexity in planetary geology, showing that worlds initially thought to be geologically dead actually harbor dynamic processes occurring beneath their surfaces. Autonomous sample analysis workflows enable robotic laboratories to process collected materials through sequences of analytical procedures that maximize scientific return while operating within strict contamination control protocols. These automated systems can recognize when samples contain materials of unusual scientific interest, adjusting their analytical procedures to focus on the most promising specimens, while preserving remaining material for future analysis. The artificial intelligence governing these decisions learns from each analysis, gradually improving its ability to identify significant findings and allocate limited analytical resources to the most scientifically valuable investigations. And now, as we drift toward the end of our gentle journey through the cosmos, we've wandered together through 100 quiet revelations about these remarkable mechanical ambassadors. From the delicate precision of their orbital dances to the patient vigilance of their electronic systems, each spacecraft carries within its circuits and sensors the accumulated dreams of our entire species. Tonight, you've heard stories of vessels that navigate by starlight, breathe through artificial lungs, and whisper their discoveries across billions of miles of cosmic silence. Let these peaceful facts about humanity's greatest explorers guide you gently into sleep, knowing that somewhere in the vast darkness above, our mechanical children continue their eternal watch, faithfully gathering the secrets of distant worlds while you rest.